Welcome everyone to this session on large-scale scientific facilities and Can you hear me now? Okay. Welcome everyone to this session talking about large-scale science facilities and diplomacy. We have an incredible selection of speakers who have worked across the world, worked internationally with partners, and are going to relate to us some of their successes and struggles and the work that they've done largely, and also how it relates to some of the science diplomacy that we've heard so much about in other parts of this conference. So first, I'm going to be introducing Laura Green. She is Chief Scientist of the National High Magnetic Field Laboratory and the Marie Kraft Professor of Physics at Florida State University. Her research is on quantum materials, focusing on fundamental studies of novel material growth and the mechanisms of unconventional superconductivity. As an advocate for diversity in science, science diplomacy, ethics, and human rights, she has held leadership roles in many science organizations nationally and internationally, including President and current Fellow of the APS, the Board of Directors, and also current Fellow for AAAS, and presently the Vice President of IUPAC, the International Union of Pure and Applied Physics for Ethics and Outreach. President Joe Biden recently appointed her to the President's Council of Advisors on Science and Technology. So if everyone could join me in welcoming Laura Green.
Thank you, Jen. This should be on. Can you hear me? Okay, thank you very much. Oh, this is crazy. Okay, so where do I aim this? Okay, good. So back? Okay. Well, it's a pleasure to be here. Thank you, Brian Bombeck's group, for coming and supporting me and my old friends. You're not hearing me? You are hearing me. Okay. So I just, I always tell my students never start a talk by apologizing, so I'm going to apologize right now. This was a last minute thing because somebody dropped out, and so here's my, and I'm with such eminent people that I truly love, and so I'm a little nervous about it. But what I'm going to do is start out, and I'm going to mostly talk about the Magnet Lab, but I'm going to start out by using two slides that I used yesterday. So a little bit about international collaborations are vital, end of statement. Some of the history and definitions of what science diplomacy is, and then I'm just going to go and talk about the Magnet Lab. And I'll be talking about the mission, the user facilities, a few of the scientific highlights. I'll probably breeze through those. We do a huge amount on education and outreach, and then I'll end up with a few slides on how we enable international collaborations and research. So this is one of the slides I stole from yesterday, which is we all know international collaborations are important, and they're vital for the future of science. It's what this whole session is about. You can't use a 45 Tesla magnet in your backyard. Okay, and so it's how do we ensure people have access to broad facilities. Diverse participation, I talked about that in some detail yesterday, and that if you have the same people that are looking at things the same way, you get stuck. So it's been proven that diverse participation, people from different backgrounds, really help further science. And then there's the science diplomacy aspect, which I talked a lot about the pitfalls yesterday, but basically, not talking about that here. It's just that it's just good at some level that we do need to communicate across borders and boundaries. At the bottom, though, I want to stress something which I really want to do, which is most American scientists don't know how to collaborate with vigilance. There is espionage there. People, it is out there, and we have to protect ourselves. So we need to train our scientists that you don't go to China with your laptop, and you have to be careful on how you check your email. What I'm interested in doing is training American scientists to do this with vigilance, with security in mind, and then convince the American government that we could do this, because we have to maintain this kind of collaboration in basic sciences and for the other problems in the 21st century. So not only do we have to do it ourselves, but we need to convince our US government that we are doing it. So otherwise we're in trouble. And then I just have this little definition that diplomacy is basically communication without wars among countries, and it goes back to the 14th century BCE. And the new diplomacy was basically, instead of having heads of states and assigned diplomats have these discussions and treaties and things like that, people started to do it. And the science diplomacy is and that's new in the 20th century. Science diplomacy is the subset where we carry, and we'll hear a lot more about it than I'm going to tell you here, where we carry people across boundaries. I mentioned yesterday that the science diplomacy was so important in the 50s, 60s, 70s, and the beginning of the 80s between the Soviet and the US physicists. And not only, even though there were 8 times the nuclear weapons than we have today, and they were very contentious, it was a Cold War. And that diversity really helped solve some important scientific problems like superconductivity. Now, I was going to try to read this journal and I couldn't get it together to do it, but I wanted to tell you about this resource. And Bill Callglazer started this center and with some other people back in 2012. And it's AAAS, but it also stands on its own. It's for science and diplomacy. So just look it up. I know you can't read that. And then the other thing that I want to stress is that it's just sciencediplomacy.org, if you're taking a picture, is this one here. So I just kind of wrote these on here. This was, I was reading it, and I realized I can't quite digest it and give you a talk on it. So I'm just going to give you the reference. So they took a bunch of, they just took a bunch of articles since 2012 and put them together. And I remember when Ray Orbach had this high-level position in the Department of Energy, and he was arguing that we should work on ITER, not that it's ever going to give us energy, but for the science diplomacy aspect. So these are discussed on some of the things here, CERN, ICTP, of course, Sesame, and we'll have some other things that are discussed in this session. So this is just a resource, and the articles, some of them are dated, but they're very, very good. Now I'm going to go on to the Magnetic Field Laboratory. And what I'm not going to talk about is here, which I talked about yesterday, is that the changing landscape, how do we, I think we all understand that now. So now I'm just going to go in and talk about the Magnet Lab, just because I hope you like it, okay? And what happened to Greg Bobinger, who's the director of the Magnet Lab, sent me this last night, that we're actually on the homepage of NSF. So the Magnet Lab, its core funding is from the National Science Foundation. No, we are not a DOE laboratory. We are not a Commerce Laboratory or FDA. We're one of the few user facilities that are actually funded by the National Science Foundation, which has great advantages, but they have less money than the DOE, so what are you going to do? So our mission that's been going on since we moved from, when we started Tallahassee and University of Florida and Los Alamos, is there's 4 missions. The first one is to operate a worldwide leading facility for high-field magnets. The second one is to do our own in-house research. I just finished the report for the annual report. There's a lot of great in-house research at the Magnet Lab. We've got a group here. For 2 reasons. One, not just to do the research, but it also brings in users from all over the world, because we have things like Ryan Bombeck's group that are doing great research. The third one is you got to be out in front in magnetic field technology, okay? Better magnets and better probes. And the fourth one, which you don't see at other laboratories, is one of the 4 missions is the education and outreach. We have an amazing facility for teaching, and if I get to that, I'll show you some of what we do here. So the Magnet Lab has 3 locations. There's 7 user facilities. So what we have there on the top is our facility in Tallahassee, where we have the world's strongest magnet, which is the 45 Tesla mag. It's been around for a while. It's a user facility, cools down all the time, people use it, absolutely reliable. And we have, and I'll go into some of the facilities, but it's very, very big. If I go from my office to my laboratory, my Apple Watch goes, yes, close another ring. So it's very big, and it's just really we're seeing. And there we have 900 megahertz, which is a 21 Tesla magnet. I'll show you some examples where we do in vivo MRI at 21 Tesla. Down in Gainesville, we have 2 amazing facilities. One is called the high B over T. It's also becoming the high B times T, because we're starting materials growth at high fields. But also here, what you can do is you can't get as low, you can't get as high field, but you can get to 21 Tesla at millikelvin temperatures. So, so that's pretty amazing. And then the other place is Los Alamos. And I like to show that picture. That's the rotor or the generator. And it was bought from the Tennessee Valley Association, and it's really big. It's being repaired right now. But it's just an amazing facility where you get absolutely reproducible, publisher, user use 101 Tesla. Okay, and we have other facilities there that do 85 Tesla and 60 Tesla, but it is amazing. And the best thing that I can tell you is that people will say, we built a 20 Tesla magnet, and then you don't hear from them again. So one of the things that we do at the Magnet Lab, and I think it's the next slide. No, I'm going to go on here. And some of our latest, greatest discoveries, our hits, were, I want to show you that in yellow there, so those are the things that we've done that are great, high field magnets, best in the world. But this 32 Tesla magnet, it's the strongest superconducting magnet in the world, and it's a user facility, okay? So we know how to do the quench protection, recool it, and it's reliable. And it's been as a user facility for a few years. And just recently, NSF gave us, I forget how many millions of dollars, we're fully funded. It's a decade-long project to just design a 40 Tesla all superconducting magnet. And if you say, oh, 32 to 40, what's the big deal? The 32 Tesla magnet stores about 25% of the energy of the 40 Tesla magnet. When you start dialing up those Teslas, and I just want to point out, nobody even has a 32 Tesla magnet. And what it opens up in the science and technology is really pretty awesome. So I'm going to say a little more about, I did this again. I know everybody does this, right? So one of the arguments we get is why, why should NSF fund a facility? Well, we got a lot of bang for the buck. I'm sorry, I'm talking too fast. In 2021, right, recently, we hosted over 1,500 users from almost 160 institutions all over the United States, and I'll stress it a little bit later, all over the world. And if you look at some of those dots there, and I'll mention also later, is that some of these dots from all over the world are people at other magnet laboratories. And we talk to each other, we collaborate, we have our secrets, and how do we get to all these, of course. So, we're going to do that. We're friendly competition. And in fact, this afternoon, the High Field Forum will be getting together just to talk about the science that we're doing and the facilities that we have. And so it is really, really an international organization. And we have a lot of publications, a lot of bang for the buck. And I also want to stress, not only is it, we get more science than cutting it all up, but you can't do this stuff in your backyard. You can't do in vivo 21 Tesla MRI. So, I always say this, about 20, depending on the user facility, 25 or 30% PIs are first-time users, and there are no user fees. So if you want to come, you just have to write a proposal. I'll show a little slide. It's not hard to write. You can talk to anybody in the Magnet Lab. They will help you write it, and then you just have to come. And I have a big house, so you're welcome to stay with me, especially if there's a football game. So these are just some of the records. I'm going to go over that again. And then I'm also bragging that I mentioned the 32T all superconducting magnet, and we made the R&D 100 this year. It really was a hero experiment. And when we go now to start building the 40T in the design phase, it's completely new territory. Okay, we're already out in front here, and it's totally new territory. And we do have a lot of international collaboration for it. So our main areas are materials, energy, and life. And what I'm going to do now is just show a few highlights because I'm trying to impress you, okay? So we'll start with some of the materials. And this was something that had a big splash, and there are whole big sessions here on this. We call it waking up superconductivity, or Lazarus superconductivity. As many of you are quite aware of, if you put a big field on a superconductor, you break up the Cooper pairs, right? And so what you do if you kill the superconductivity, what was found in this heavy fermion material, uranium tellurium-2, is that, now this picture, I hate pointing because there's two screens here. I'll just talk about it. So the blue part at the bottom is where it's superconducting. And what we have along that x-axis is the angle at which the field is being applied. This work has a high enough field that was done in the DC facility in Tallahassee and the pulse field facility in New Mexico, in Los Alamos. And we see that at a certain angle, the superconductivity remains up at 0 angle, and then it goes up to this magnetic state that's in red. But if we go to this funny angle, you go up and above 30-some Tesla, 40 Tesla, it starts superconducting again. This was totally unheard of. It's not predicted. You guys are working on it. Nobody understands it. And so this is just to show you that the basic science of putting a high field on something can really astound you. And there's a lot of people working on this now, and we're trying to figure it out. This is one, because it's a big thing right now, is that this is an example in the electromagnetic resonance facility of doing terahertz pumping, that you go from an antiferromagnetic to a non-magnetic, weakly diamagnetic material, and you can send signals back and forth. So you're terahertz pumping, and this is the fastest, it needs to be scaled, of course, but this is the fastest spintronic type device because it doesn't use super exchange. I also like to bring this up in physics meetings, is that when Fabiola Giannotti gives a talk, the Magnet Lab is all over it. Because, for instance, one of the examples is that their high luminosity upgrade that they're working on right now, they were replacing niobium titanium with one of the A15 compounds because of the work that was done on the Magnet Lab. And that little change, going from the niobium titanium random alloy to the compound, which is very difficult to use, increased the critical current so much that it will give the high luminosity upgrade a factor of 10 in luminosity. And we've developed a new material within the past couple of years that's hafnium doped niobium-310, that's even a higher critical current, critical field. And we believe that will also be used. And this is a collaboration, international collaboration. The materials we developed with the Magnet Lab. We work with Fermilab and with LBNL, and now Brookhaven is part of the group. So it really covers a lot of different things. Now we're going to talk about energy. And most condensed matter people have no idea about this. If you're a chemist, you do know about it. And this, if I don't get any more except past this ion cyclotron resonance, I'll be happy. This is a mass spectrometer on really high level of steroids. Okay? It's unbelievable. It gives you mass spectrometry to the resolution of about 1 electron. That's about 2,000 times less massive than a proton. Okay, so there's like that dotted line with the spiky thing over on the right, the green dotted line. That's quantum time of flight spectrometry, and that's the only competing technique. There are other ICRs, but no one has this resolution. It was invented to look at oil because oil is the most complex fluid on the planet. And to show some example, by looking at this high resolution, if Exxon and BP both drill a well in the Gulf, and they want to know if they hit the same reserve or not. So this, you can just do a spit of this stuff. You spit a little oil in a magnet and you chirp it. And it gives you that kind of resolution. And also forensics. So if we don't know who spilled the oil, we can tell you what oil head it came from. Okay, years and years labor, because they're so complex. Is there a little more of this, that? Very, very complex fluids. It's also been applied to proteinomics. One of the famous ones that we've worked on is the P53 protein. As many of you know, that functionality can be determined by how it folds. So how it folds on a surface, replacing deuterium, replacing the hydrogen with deuterium, we can tell how the P53 protein folds if it's going from healthy, neoplastic, or malignant protein. And then I'll show you a couple examples here is climate change and sustainability. The second most complex fluid on the planet is dissolved organic carbon. And I'll just show you some examples coming up here. So I'd like to talk about this in the ion cyclotron resonance area. Amy McKenna's been I think this is her slide. So there's a couple of things that we do here, and other people at the Magnet Lab in Florida State and all over the world work on this. And on the left, we can study what controls the dissolved organic compounds, organic matter, all over the Arctic. You can look at it as a matter of time and location and track what's going on in the Arctic with climate change. Also, if you want to figure out if someone is using dangerous chemicals on the road, you want to make sure that the organic matter that's in the asphalt, will it dissolve in water or not? If it dissolves in water, it can affect the groundwater. And there's a lot of work that we're doing in Florida in groundwater because I don't have time to talk about it, but no one else can tell this stuff. We're happy that this company is using this kind of asphalt because it looks so good, but is it polluting our aquifers? And we can actually tell the difference if it's an island shape organic mixture or an archipelago, and one dissolves and one doesn't. And you need that kind of resolution to get there. And this is one that just came out just a few months ago, which is we always thought that plastic bags were forever chemicals, the PFAS chemicals. And what they determined in ion cyclotron resonance was that the PFAS chemicals actually do break down. And they did look at CVS bags and I don't know what other bags, and et cetera. And what it breaks down to, whether it makes it more or less dangerous, is still under survey. But the point is that no one could even tell that these PFAS were breaking down. So now we're going to go into some of the examples of life. So we did materials, and we're going to go into life. And here's the first example is, how many of you have been inside of you probably all have. You all have been in MRIs, except you young kids, right? Probably anyone over 25 has been in an MRI, right? And the coolest thing about an MRI is that you get to go inside of a superconducting magnet, right? Very cool. But it's also about 4 Tesla, too, depending on what hospital you're at. We're doing this at 21 Tesla. So what does 21 Tesla do? Well, for one thing, it gives you a higher resolution because when you pick up things in MRI, you put things in magnetic fields, you line up the water, you're looking at the hydrogen, and then you have a resonance thing that they put in RF field, and that's how you do the spectrometry. Okay, it's with the RF field. Now at 21 Tesla, you don't want to be in there too long. It's not as bad as a microwave, but you can still do it with humans. But look what you can do here. By going from 21 Tesla, you can now go from millimeter to micron size resolution. Okay, so that's really important. But the other thing, why is that important also on living things? If you're interested in plaque amyloid detection, no one can detect it earlier than the magnet lab. And these are still rats, so we haven't scaled up to people yet. But in fact, what happens with plaque amyloids, they make little tiny microhemorrhages. So the plan will be is that if you have some Parkinson's or Alzheimer symptoms, you can go in and see, are you developing these microhemorrhages or not? So it's going to be very important to tell those things. Another one is that we talk about, instead of looking at hydrogen, we can unlock the periodic table and look at other things besides hydrogen. And here's everybody's favorite example, which is instead of looking at hydrogen, let's look at sodium. Sodium is much heavier than hydrogen, so it's going to have a much lower resonance condition, much lower resolution, but in fact, you can see where the sodium is, okay? So here's an example on the left. I also learned when I got to the magnet lab is you can buy a mouse with brain cancer, okay? So that's imaging the sodium in a mouse's brain, and there's a tumor there. And what you do is you determine a method of chemotherapy, and you treat the mouse, and you image it 4 days later. And you continue this until the sodium lights up. What does that mean? That means that it's absorbing sodium. It's uptaking sodium. Well, it turns out that when cells are dying, they actually uptake sodium. It's not completely understood. So if we see that tumor light up, it's uptaking sodium, meaning the cells are probably dying, giving you some confidence with that chemotherapy regime. Okay, and here's another one. This is sort of cool. This is fairly new. This is at 17.6 Tesla. This is a living rat brain where they can actually tag the stem cell therapy with gadolinium and see how it's going. Okay, and I don't have time to go into it, but this one can. How do these stem cells respond to brain damage and a stroke? 10 more minutes? Good. Then I'm going to go. Okay. Okay. So I'm going to jump over a whole lot of things because I only have 643 slides. Anyhow, so go and sign up. Pick out a magnet. We'll help you write the proposal. I'm going to breeze through a couple things with education outreach just to impress you. We do a lot of participating, thousands of people in the Florida area and internationally. I have a slide on international education coming up. Lots of workforce development. We really worry about postdocs and students and research experience for undergraduates. And this is the impact. I think these slides will be posted. You're welcome to look this up or ask me. And we also do a lot of web education. They're worldwide, between bridging the scientists and public affairs and lots of partners. And I want to sort of move on. You can go look these up, Fields Magazine, See Through Science. At the March meeting a few years ago, we had a subatomic smackdown where people all over the world, it was a collaboration with CERN, people all over the world would vote for their favorite particle. Was it a photon, a neutron? And it was popular. We had over 2,000 views. We just had our open house on February 25th. We had over 12,000 people, and there's my niece being floated on a magnet, and it's just a heck of a lot of fun, okay? So I recommend coming there. Now I'm gonna go to the international aspect a little bit more. So the Magnet Lab, we are international, and we love being international, and we have employees from 60 different countries. And there's all kinds of opportunities. You can come and be a user. You can apply for jobs. We have a Theory Winter School. We have a summer school to teach people how to use equipment, and not just magnets, how to run a lock-in amplifier. And we have people that we bring in from all over that are external advisory board members and our user committee members. And we do support people. We have facilities for bringing in visiting scientists. You can apply for those things. We have, and as I mentioned, if you're a first-time user, we'll help you out to get there. And if you haven't used the Magnet Lab, if your country or your area hasn't used the Magnet Lab, you get a little higher on our list for diversity aspects. And then we have a dependent travel grant program to help our people that if they want to go to the March meeting, it helps them get childcare. And we have international support for both short and long term, and these are some of the grants. But I think I'm going to bring out that there's also some challenges, okay? And the challenges that we have nowadays, of course, the visa issues. It's even hard to get into the US with a tourist visa nowadays. A working visa, especially if you're from certain countries, is just harder. And with the increased international tensions, it's even harder than it was a year ago. I'm co-chairing a task force at Florida State University that MagLab is some of our scientists are very involved in. And what we're doing is twinning with a university, Beketov University in Kharkiv. And we're running into difficulties there, right? We can't give them access to all of our libraries, for instance. So we're also working with Loughborough University in the UK and trying to work around there. And what we're going to be doing is just sharing best practices, have some talks. They do a lot of work in water purification, so they're interested in the ion cyclotron resonance work that I mentioned before. I also mentioned earlier about the global cooperation, and if you want to come to our meeting, I think it's at 3 o'clock. You have to ask me where it is because I don't remember. But as I said, the high field magnet people do collaborate all over the world. This is our international impact in education. And just to show you that we have this is old data from 2015, I'm sure it's a lot higher now, but we have millions of views from all over the world. It lists some of the countries on the far right there. And so we really make an effort to try to reach people all over the world in education. So I think that's enough, but I hope I got across that the importance of this, and since I don't have Sesame to talk about, I'm talking about the Magnet Lab. And so we do science, engineering, medicine, physics, chemistry, biology, ecology, geology, sustainability, psychology, education, outreach, and public engagement, which makes us unique. So come and visit. Thank you very much.
Thank you so much for that, Laura. Are there any questions from the audience?
Hi, Cheryl.
So this not taking your laptop to China. So how do you deal, so you've got to give a talk, you've got slides.
Yes.
So you send those ahead or something? How do you actually get around?
So I've been using for years, and now the MagLab, and certainly if you work at Los Alamos, you have burners, right? So you have burners. So I get a wiped computer. I have some old ones at home, or the Magnet Lab will give me one. And I just put on there what I need. And I don't check my MagLab email. I forward it to something else, et cetera. So I told the story yesterday, which was really true. It's one of our scientists who's here, I don't know, he's not in this room, was giving a talk in Wuhan, which is their pulse field facility. We're friends with these guys. I love them. They're great guys. But he went out to dinner. When he came back, he opened up his laptop and it booted up in Chinese. If you go through any of this, as president of the American Physical Society and a lot of the stuff I do, going all over the world, I have been trained that you're supposed to recognize that the person who's cleaning your room is going to be a spy. It's not the scientists that are necessarily doing this, but we have to figure out how to do it. Because, it astounds me that typical American professors don't know that you're not supposed to do that. So we need to educate Americans to do this and convince our government we can do this. Because if we can't do the international collaboration, as David Pines once said about China, we're not going to beat them. Let's hope they take us along. So I don't know if that's true anymore, but we need the diversity, the facilities, and the science diplomacy. So we have to figure out how to do it. So.
Thank you. Are there other questions from the audience?
Uh-oh. Hi, Dirk.
This is a quasi-scientific question. So what is the physiological impact of 21 Tesla on the poor mouse who was alive?
They're fine.
Yeah?
They're fine. They give them, sometimes they put them to sleep, and when they don't, they give them this, the 900 Tesla, they give them a little bite bar that calms them down. And they go running around afterwards. Yeah. No, 21 Tesla is not, the only thing that's bad about 21 Tesla is the RF frequency you have to do to use the, the RF frequency it's not that dangerous, but it's not as low frequency as normal commercial MRIs. So it's not as bad as a microwave oven, but it can heat a little bit.
Yeah, okay.
So.
The equivalent in centigrades is about 21 Kelvin, actually, if you let it act on Bohr magneton, right?
Yeah, but the mice are just fine. They just, there's not a problem. They go there and they play chess afterwards, and they're good. So.
Thanks.
Thank you. Anyone else? I was curious if you could speak at all to, are there countries that are able to take advantage of this technology and then continue on in other things not related to the Magnet Lab, like once that relationship has been formed?
Absolutely. I mean, what we train people to do at the Magnet Lab, cryogenic abilities, communication, right? We teach people how to give talks and write papers, building equipment, winding magnets. These are unbelievable. In fact, what we want to do is we train so many people at the Magnet Lab, we want to find a way to give them certificates and take it home with them across the United States and their own home countries. So there's a lot of training that goes into huge, not just the education outreach that I mentioned, but also in the laboratories. There's a huge amount of training. And we got MagLab people all over the world. So, okay.
Thank you. Let's thank our speaker again. Bob, if you want to put that up. There you go.
Watch what I say.
I don't think it's on yet. Next up, we are pleased to welcome Robert Kirschner. He is the Executive Director of the 30-Meter International Observatory, a project to build an extremely large optical and infrared telescope. He was a professor of astronomy at Harvard for 30 years before taking up the job. He is a member of the National Academy of Sciences and a winner of the Wolf Prize in Physics for his work leading to the discovery of cosmic acceleration. Thank you. Let's welcome.
That's better. Oh yeah, that's much better. And the room is too big, so it echoes. That means I have to speak a little slower. But that's all right. Okay, I'm Bob Kirshner, and I was at the Gordon and Betty Moore Foundation before I switched over to do this job at the 30-meter telescope. So a number of the people here have gotten grants from the Gordon and Betty Moore Foundation in the field of quantum materials. All right. This is an image of what we're planning to build. It's the 30-meter diameter telescope. The mirror is a single paraboloid, but it's made up of hexagonal segments. They're about 1.4 meters across, and they're separated by about 1.5 millimeters. So it's a nearly filled aperture made up of these hexagons. And now, forward. And Laura gave a very nice talk about the range of science that the Magnet Lab affects. Here I want to emphasize, because I'm at the physics meeting, the fundamental physics that you can do with an astronomical telescope. You know, the question of what is the world made of has been one that people have been working on for a long time. This was a former hypothesis that it was air, earth, fire, and water. I just came back from India, where when I showed this slide, they said, oh, no. In our tradition, there's also vacuum, which is, of course, exactly the right thing, because that's what I'm going to be talking about. Okay, so we're looking at the fundamental materials of the world, and we also have a history of the world. The telescope is a no-nonsense time machine, because the light that you see from distant objects was emitted a long time ago. With the big telescopes and their sensitivity, we can see very far back into the history of the cosmic expansion. So we have this story that there were quantum fluctuations in the early universe that somehow led to the inflationary world, that we can see the glow from the microwave background. And then somewhere in there, galaxies began to form. Big telescopes will be very useful for looking at the early formation of galaxies. And you can use them and the stars that are in them as tracers of cosmic expansion. And so by doing that, as I'll say in a second, we found something quite surprising, which is that the universe is not dominated by matter. It's not dominated even by the dark matter that we know is out there. It's dominated by a vacuum energy, which is maybe something very much like the cosmological constant, or like those Sanskrit myths. Because we see today cosmic acceleration, despite the presence of matter and the effects of gravity over time. So here's a little more quantitative version of the same sort of idea. Looking back to the early time of inflation, thinking about the first stars, and then the development of galaxies, planets, and of course, possibly biology in places around the universe. So we now have a quantitative picture. We think it's about 14 billion years back to the Big Bang, and that the era of acceleration is the last 6 billion years, more or less. Okay, I want to make the link to technology. The telescope, of course, is a technology, and the detectors are a very important aspect of this. In the old days, of course, it was the human eye, then photographic plates, and then beginning in the 1990s, charged-coupled devices became common. This is my thesis advisor, Bev Oak, and he is holding in his hand the world's largest CCD for astronomical use at 0.24 megapixels. So it's just a reminder of how rapidly the technology has developed, that this was a big detector at the time, and the data taken with these detectors we thought were big data. Okay, and just to show where that's gone, go, forward. Oh, yes. And of course, well, I was at the Moore Foundation, so I have to show you this. So here's a plot of of Moore's Law that shows the processors that you might have bought when you were, when you were a graduate student, and the ones that you can get today almost on the horizontal axis from 1970 up to about 2020. You can see that the exponential increase in the number of transistors on a chip has gone up, and the technology for making those transistors is exactly the technology for making the detectors, these CCD detectors that I've been talking about for astronomy. So here's an example of Moore's Law at work. Instead of that little thing that's the size of your fingernail, here's John Tonry with almost state-of-the-art camera, which is up in the gigapixel range. So the technology has been zooming along, and it means that the telescopes ought to be improved as well to match what we can now do with the detectors. So I'm going to just mention one thing, which is looking at exploding stars, supernovae. So here's a galaxy up there, and you see this bright dot down below. That's one star which is exploding, and during about a month is very bright. It turns out you can calibrate the brightness of those and use them as distance indicators, which has been a very good thing to do. If you want to know the whole story, you can read my book, which is now available in Spanish, Portuguese, Japanese, Chinese, and for some inexplicable reason, Czech. I don't know. Anyway, but it did lead to the understanding that the universe was not just decelerating under the effects of gravity, as you might have expected, but accelerating. And we have this guy here at the meeting who pretends to be Einstein. Have you had your picture taken with him yet? I did. And this is a pretty good model. I want to get him to hold lambda, the symbol for the cosmological constant, and take his picture again. Anyway, this was a big deal about 20 years ago, where we showed that underlying field, the vacuum energy, is really an important component of the universe. In fact, if you take a look at this, you'll see that atoms compose about 4% of the universe. So everything on the periodic table, that's a pretty small fraction of the total. We know there's also dark matter, which is not baryonic, not made of the particles of the periodic table, and we know it's there because we see its gravitational effects in clusters and other places. And then this dark energy that I've been talking about that's required to account for cosmic acceleration has to be in the majority of the universe today. So if you were a dean, maybe some of you have been a dean, this would tell you a little bit how to allocate resources. Atoms, that would be chemistry, let's say, 4% of the budget. Cold dark matter, well, okay, that's experimental physics. Well, not yet. It's still astronomy, but people who are doing the experimental physics are hoping to see it. Anyway, about a quarter of your budget, and then, 3/4 would be about the right amount for the astrophysical work. Okay, the technology of telescopes has led to really big ideas in the world, of course. Here's Galileo at the Venetian resort next door. Oh, sorry, no, this is actually in Venice with his telescope and demonstrating it to the people out in front of the Doge's palace. Galileo said, "All truths are easy to understand once they are discovered. The point is to discover them." And the point here is that the telescopes that we're interested in are for discovery, out at the edge of understanding. At that point, just showing that the moon was made of a substance like that of Earth was a big deal. This business of cosmic acceleration turned out to be a very good thing for my graduate students who won the Nobel Prize. I got to stand on the stage, though. Or as I sometimes say, I could only think of one thing better. Well, anyway. All right, so let's talk about the future. Let's talk about these telescopes. Because we're probing fundamental physics in this slightly indirect way, and we want to do it better. Well, the National Science Board, we've got a National Science Board. They govern the National Science Foundation, and they wrote a decadal vision statement. That's good for them. They say, for the U.S. to remain a global leader, America's researchers must have access to facilities that will astonish the world. Tools that let them see further, faster, and deeper. Good. And then they say at the end, the U.S. must cooperate with other countries, so that's the point of this session here, such that U.S. researchers can participate fully, help set the agenda, and share equitably in the results. Research infrastructure needs for 2030 and beyond will range from desktop microscopes to billion-dollar telescopes. So I'm here to tell you about a billion-dollar telescope, and we are going to ask the NSF for $1.8 billion. Okay, so this is our answer to that vision. This is a conception of what the telescope would look like. It has a novel kind of enclosure. It has that segmented mirror that I was talking about, which is just a natural extension of the current state of the art. The Keck telescopes on Mauna Kea in Hawaii are 10-meter telescopes that have this kind of technology. They have hexagonal mirror segments that are controlled so that it makes a single mirror surface. So you're controlling it to a wavelength of light in order to have a coherent image. And the 30-meter telescope is really big. And I want to emphasize that part of the reason why you want to do this, instead of making a lot of medium-sized telescopes, is that there are things that scale approximately as the fourth power of the diameter. You can imagine something that scales like the square. That would be, of course, the area and the flux collected. But the other thing is, if you can do adaptive optics so that you work to the diffraction limit of the telescope, which we know how to do now, and which we do at the Keck telescope pretty much all the time, then the image gets sharper by d in each direction. So that's another d squared. The signal to noise goes like the fourth power of the telescope size. So that's part of the motivation, the scaling, for making one gigantic telescope instead of a forest of small ones. And there's a human over there at the same scale, just to, you know, well, if the business of not being made of the substance that makes up most of the universe didn't make you feel humble, seeing how small you are compared to that mirror surely will. Okay, and here's Moore's law for telescopes, just for fun. If you start at Galileo's telescope, you'll see down on the horizontal axis 1700, 1800, 1900, 2000. The progress is exponential. As you can see, the scale here is centimeters, meters, 100 meter, no, yeah, 10 meters scale. Oh, sorry, it was in, it's in square meters. Yeah, that's the area. And you can see that it has been increasing over time. And here we are now, after 2000, you can see that the time has come. What you see up there, it says Keck, VLT. Those are state-of-the-art today telescopes. And the next cluster are the telescopes we want to build, of which TMT is one. And you can see that when they made this plot, which was 2010, we were a little ahead of the curve. And in fact, it won't be until 2030 that we actually have this thing working. Okay, but anyway, we're on the path. But just because you have an exponential change like this doesn't mean it's going to happen by itself. It means you have to do the work and you have to pay the cost of these very expensive facilities. Okay, so here's the international part, and here's the story about financing this gigantic telescope. The partners in the TMT, the 30-meter telescope, are the US, Canada, Japan, India, And we've had participation by China up until now. They may be withdrawing soon. And here are the different parts of the telescope that people have contributed to or made promises to do. So India's been very good on the observatory software. I didn't know where to put that on here. There are many science instruments. Maybe the simplest thing to think about is that the enclosure, that funny structure around the telescope, is going to be contributed by Canada mostly. The telescope structure, the blue stuff that points the mirror around, is being contributed mostly by Japan. The mirrors are being made in the US, in Japan, and in India. So it's really is an international thing. Now, when I say the US, we have a project office in Pasadena that I'm in charge of, I guess. We contract for some of the things using money that has been contributed by the partners, and also by the universities in the US. The members of the telescope are the University of California, all of those University of California campuses, system really, and Caltech. And they have gotten a substantial part of their funding through the Gordon and Betty Moore Foundation. So that's been a good start for the telescope. And what we need now to be the US part is a contribution from the US National Science Foundation. So the current status is that there's been a preliminary design review, there's been a memo that puts us in the MREFC queue, if you know what that thing is, and we're on the road toward funding this telescope at a large scale from the NSF. This was the top priority of the National Research Council's assessment of the field in 2020. They say because of the powerful potential that large telescopes with diffraction-limited adaptive optics, so that was the point I was making a few minutes ago, have for astronomy, and because of the readiness of these projects. We've been working on it for 10 years without the NSF making a major contribution. The survey's priority for a frontier ground-based observatory is a significant US investment in the Giant Magellan Telescope, that's the other one being built for the Southern Hemisphere, and the 30-meter telescope, that's the one we hope to site in the Northern Hemisphere, ideally as components of a coordinated US extremely large telescope program. So there'll be a telescope in the north and a telescope in the south. We could look at the entire sky from US-led facilities. And here's that picture. What's shown up in the upper left is a conception of the 30-meter telescope. What's shown in the lower right is a conception of the Giant Magellan Telescope using a different technology for the mirror fabrication. And what's shown in purple is the part of the sky that you could see for TMT if it's located on Mauna Kea in Hawaii. What's shown in blue down at the bottom is the part of the sky that you can see from Las Campanas in Chile, where the GMT will go. And the band in between you can see from both places. So there are plenty of overlap, as well as the range of being able to see the entire sky. If you think about it, you think what are interesting things you might like to do? Transient events like LIGO sources, where there are neutron stars banging into each other. We know that they give off light, at least one of them did, and we know that the light is not very bright and fades quite quickly. So you have to be able to go quickly to any part of the sky and make very sensitive measurements, and this system would be capable of doing that. Another example is we're very interested in the nearest stars, the planets around the nearest stars that might be like the Earth. We don't know which ones they're going to be, whether they're going to be in the north or they're going to be in the south. You'd like to be able to study a handful of those rare objects wherever they are with this kind of system. And for other aspects where you're doing cosmology, it doesn't matter quite so much. One place is more or less like another, but the telescopes will have different excellences. They're going to have slightly different instrumentation on each one, and they're going to be able to complement one another. Okay, so this Astro 2020 said, well, here's the scientific panorama, and we tried to see how that matches up with the telescopes. Astro 2020 said both projects, that meant the GMT and the TMT, both projects are essential for keeping the US community's global scientific leadership. The US has been the leader in observational astronomy since the times of George Ellery Hale, who built the telescopes at Mount Wilson, the 60-inch, the 100-inch, and then later the 200-inch at Palomar, set the standard for the world and opened up this field. The telescopes on Mauna Kea today, the Keck telescopes, Gemini, the Japanese Subaru telescopes, are the state-of-the-art as well. But Europe has certainly come up, and they've built a very excellent facility in Chile. And if we don't take the next step, we're not going to be the leaders in coming decades. So what are we going to do? Well, as I described, one thing that would be really interesting would be to study the atmosphere of a planet around a nearby star, where the planet was kind of like Earth, had the surface gravity of Earth, the temperature of Earth. We can do that with this kind of telescope. We even know some of the targets that we might work on. I mentioned, then under the category of new messengers, gravitational wave events, I mentioned that. They could happen anywhere on the sky. And then you're interested in this problem that I described at the beginning, the composition of the universe, the dark matter, and the dark energy. Moving over to the right side, it's what the panel called cosmic ecosystems. It turns out that things are quite complicated, and that the energy generation stars produces the heavy elements. They become the material for the next generation of stars, and of course, for planets. And we know that in the centers of galaxies, there are giant black holes, and we know that some stars collapse to become black holes. So there's a whole range of topics that we'd like to be able to work on. Okay. And so I hope I've persuaded you a little bit that this is not just for astronomy. This is going to touch on deep questions of fundamental physics. It's going to touch on the geology and the atmospheres of exoplanets. It even touches on physical chemistry, you know, what happens at these low-density places where there's ice and dust. And I don't want to promise too much, but it could revolutionize biology. Nature is doing experiments in ways that exceed our imagination. There are lots of planets out there, and it's up to us to follow along and see in what ways those complicated stories work out. They're not all going to work out like Earth, and we know that. But nevertheless, here's what some people think will happen. The text here says, they just built a way more powerful telescope. Everyone put on some pants. Okay, well, that's not what we're going to do, but we will look at the chemistry of the atmospheres. Let me just show you what this improved resolution is worth. Here's an image that we've constructed, and you've seen these beautiful images from JWST, the James Webb Space Telescope. The James Webb Space Telescope is 6.5 meters. It does operate at the diffraction limit at a wavelength of about 1 micron. This telescope is bigger, and it's going to produce sharper images. It's going to be faster because it collects 20 times as much light, and in some ways it'll be better. Some of the instruments will have a bigger field of view, but the real point is it's going to be a lot easier to maintain it. The James Webb Space Telescope is, at the Lagrange point. You can't go there and fix it, whereas this telescope, we hope, will be on a mountain on Earth that you could go up to for the next 50 years and put state-of-the-art today's instruments on it. So easier access to build, fix, and improve. So this set of images shows something at what you might imagine to be ground-based resolution. This is Hubble Space Telescope resolution, so much better, and we're very glad to have it. The next step is JWST resolution, and that's about where the state of the art is now. And this is 4 times better. This is what we expect the effectiveness of this telescope to be. What's a problem where that really buys you a lot? Well, there are many such problems where improved resolution helps you measure a faint thing next to a bright thing, like a planet next to a star, or a supernova next to a galaxy, or the properties of a galaxy at high redshift. It also could, for example, help you probe the nature of dark matter. We know it's there, but we don't know how clumpy it is, and we know it can produce images like this ring by general relativity. Well, you know from relativity that the presence of matter warps the space. When you look at a distant galaxy through a lensing object, you can get these rings, which happens from time to time. On the left side is the resolution that you get with an 8-meter telescope, sort of today's telescope. And on the right, is a simulation of what you would get with a 30-meter telescope. And by looking at the details of the imaging, you can tell whether the dark matter is smooth or clumpy. That's the point here. So you learn some aspects of the dark matter. Even though you can't see the dark matter, you're not seeing the matter, you see the effects of it. And you can tell whether it's clumped into objects that are as big as a 10,000 solar masses. Okay. One more place where this application of high resolution will help is in the center of our own galaxy. With the Keck telescope, you can do it. But with a 30-meter telescope, it'll go right better. So here is the Keck and current adaptive optics, and those are images of stars at the center of our galaxy. You can see they're going in ellipses. This reminds you of Kepler's laws, because there is a massive object in there. There's a massive black hole in the center of our galaxy, and it has been measured over the past decades by Andrea Getz and her colleagues at the Keck telescope. But at the 30-meter, they have made a simulation. You'll see more stars, you'll see them in closer, and you'll move beyond things like knowing there's a black hole there to actually getting to tests of general relativity. So that turned out to be a good thing too. Here's Andrea with her Nobel Prize from a couple of years ago. So this is the kind of thing we want to keep US astronomers in the game of doing the forefront research, and building this telescope is part of that story. Okay, I already said it was an international partnership. Okay, and our partners have contributed a lot. I was in India last week, and they're in the process. Well, this is in the US, where we're working on making the mirrors. The company that does it is the same company that made the Keck mirrors, the same company that made the JWST mirrors. They're making our mirrors. This is the A team. And our colleagues from India spent a whole year there learning how to do this. And they've now set up, well, all right, never mind that. They've set up this new factory facility in India near Bangalore to do this. I was there last week, and it's still a clean, beautiful building at the moment. It's a better building than Coherent Optical has in Fremont, California, because they started from scratch. It's bigger, it's cleaner, and they're getting the equipment from the US to put in here so that they're able to go and do this. So here I was last week, and they're showing me some of the bits of equipment that are being made in India. So our international partners are doing a lot of in-kind work. They're also contributing cash. Okay, well, maybe that's enough. This is a little bit of hyperbole, but if you think about it, this resolution, improvement in resolution, is a big step forward, and as big a step from Hubble as Galileo's telescope was back in the 1600s. So here's the idea. We're going to have images of galaxies at redshift 2 that are going to be as detailed as shown here. Okay, well, that's it. I was struck by something that Tom Rosenbaum, who's the president at Caltech, said after going up to a visit at Palomar. He said, "It's a powerful reminder of the scientific payoffs that can result from the combination of persistence and ingenuity built on the foundation of engineering prowess." And that's what we intend to do in building the TMT. Thank you.
Thank you, Bob. Do we have questions?
So I think you've also got to engage in some domestic diplomacy because of the trouble
Yeah.
with the indigenous people
Yeah.
who don't want you to put this telescope on the top of Mauna Kea.
Correct.
I was there last July. I saw their encampment,
Yes.
which is now moved to the side.
Yes.
Please comment on that.
Yes, let me tell you what we're doing. You've touched on a very important point, which is that for 50 years there's been astronomy in Hawaii without much consultation of the native Hawaiians. This has got to change, and we're going to change it. Our contribution is to engage with that community, the people who were sitting on the road. We used to mostly talk to the business community and the government people and got all the approvals. That was okay, you got to do that. But building trust and a real engagement with the native population is certainly what we are doing now. The government of Hawaii is also doing some things. The University of Hawaii used to run the top of the mountain. That's going to stop, and there's going to be a new Mauna Kea Stewardship Authority, which I think is a great idea. They are going to be in charge of it. It includes a lot of different stakeholders, including representatives of the native Hawaiian population. So I think there's a real vehicle for them to have the power to affect what happens up on the mountain. The complaints of the native population are not mostly about astronomy. They're mostly about the injustice over the last few hundred years, and especially since the US took over in the time of President McKinley. So the status of native Hawaiians is not that great. There are broken promises on housing, education is poor, healthcare is poor, employment's bad. We can't change all of those things, but I think we can help push the state government in the right direction. So I had a chance to talk to the governor last month, and I talked to the person who's the chairman of this Mauna Kea Stewardship Authority. I think that's the vehicle for doing what you're talking about, which is making a different kind of agreement, a better compact with the locals on the use of their mountain.
Thank you. That was a great question.
Yeah, it is. I should have said that.
Yes.
It was a very inspiring talk. Thank you.
Good.
Just one simple question. I've used this before, but you have that pie chart.
Yeah.
That has, dark energy, dark matter,
Yeah.
and atoms. How do you come up with those numbers?
Yeah, that's from a model of the cosmic expansion story that is based on the supernovae and the redshifts of the galaxies that they're in, so the distance and the history of cosmic expansion, plus the story from the microwave background. It turns out the microwave background provides important information on the properties of the composition. You get fluctuations in the microwave background that depend on the ratio of the matter to the radiation. And by putting all of this stuff together in a fairly simple way, you get a solution that both matches the difference between the dark energy and the dark matter and the sum. That's algebra, and they do intersect, which is a good thing. And the locus of that intersection is what gives you this story. So it's based on a model that's kind of maybe oversimplified. We don't know that we understand the dark energy fully, and maybe we don't understand the dark matter fully. Maybe it has some self-interacting part. But for the simplest physical model, it's not too far. And if I'd had a little more time, I would have taken you down that path. But it comes from a combination of the microwave background data and the history of expansion from the supernovae. Yeah.
We have time for one more quick question.
Yes, thanks for a wonderful, exciting presentation. I had a question. I think that in recent times, it's been discovered that stars and galaxies have been forming earlier in the universe than some people expected.
Yeah.
So I'm wondering what the TMT may be able to contribute to that particular question.
Yeah. So the point is that the JWST observations, which people have been making, show that contrary to expectations, the galaxies at very high redshift, so long ago, early in the history of the universe, were actually quite mature. Whereas we thought they would still be in the process of assembling, would be a way to think about it. And we certainly will not have the infrared capability that JWST has, but the ultraviolet light from those objects will be accessible to us, and that'll be a good thing as a complement to the story of what kind of star formation is going on, you know, whether there's black holes or stars that are causing the ejections of matter, all that stuff that we're so interested in. So we're interested in getting that. We're certainly going to have the sensitivity, an unprecedented sensitivity, and I think adding the ultraviolet part is what we'll be able to do.
Thank you so much.
Okay.
Our speaker again.
I feel like I should take this laptop. It has my stuff on it, but not to China.
I'd like to welcome our next speaker, who's going to be speaking both on CERN with time for questions, and then Sesame with time for questions on that at the end. Eliezer Rabinovich is a theoretical physicist from Hebrew University in Jerusalem. His area of research is the study of phases of matter of gravity. He has served as vice president of the CERN Council, and since 2022, the president of the CERN Council. He was twice the vice president of the Sesame Council, and was awarded, with others, the 2019 AAAS Prize for Science Diplomacy. And we're very excited to hear him speak.
Okay, how does this work?
Green?
This one, green and backward?
Just that one, and then I think that's, yes.
Okay, I'll ask the question. Do you hear me? Okay. So, thanks for inviting me here. My talk will mention science, but I will concentrate on the issues of diplomacy and on international collaboration, different extent in the different talks. So this is a tale of two accelerators which are actually tied together. One is CERN and the other is Sesame, so I start with CERN. So I'll start by putting things in a perspective. So we have at CERN a competition for high schools all over the world, and ask them to suggest to CERN an experiment which can be performed at CERN. And one picks every year a few of the high schools. And here I learned that in December last year, 2022, a group from Cairo won, high school from Cairo. So I was very interested to meet them. I went there and I asked the group, why actually are you studying physics? So Rashid, which is a tall guy behind me in the photo, answered, because I want to understand the universe. And this echoed deeply with me, because this was the banal answer I gave my to-be PhD advisor when he asked me, why do you want to be my student? And I told her, I'm sorry, I only have a banal answer I can tell you, and it was that. And this, I think, touches about the general human aspect that we have here. And let me put it even in a larger context, which after the talk we heard from Bob before is even more suitable. And that is the following. Okay, here is the whole universe from the smallest to the largest. And I see here around 12,000 American and international physicists who have the pretense to understand this whole universe. And I want us to appreciate that for a moment, because most of us are actually between 1 and 3 meters. And we want to understand things till 10 to the minus 33 centimeters, or to the extent of maybe 20 billion light years to the universe. I hope you realize how much pretense there is in it. And nevertheless, people from thousands of years ago thought that the human race is up to that. Now, nobody respects this principle, which is NOH, which is nobody owes humanity. I don't think anybody owes humanity that we can have these concise 30-minute lectures describing the whole universe. And nevertheless, it seems to work. There are equations, that's it, one slide, helps to explain a lot of what's going on in the universe. Then we look at the level of professionalism which we have obtained. So we have this unbelievable accuracy in understanding the electromagnetic force, having things where theory and experiment agree to about 12% after the digit, and I would challenge any other science to be able to come close to that with 2 input parameters, the mass of the electron and its charge. But once you measure those, you can calculate, you can measure in a laboratory, you can do both things, you can measure and you can calculate, and you get this fantastic agreement. So this is our 5th symphony. The other basic force, the weak force, you can do, I'm always showing the best case, by the way. Okay, there are more complicated issues in each of them. You can do the weak interactions, you can do things with a precision of 0.1%. Then if you go to the colored force, a third of the fundamental forces, you can do things within 1%. And when I was a child, this was undreamable that these things could actually be done. Then you can put all particles that we have measured, I emphasize particles, that we have measured on one slide as well, which is amazing. I say here, I put it that sometimes they don't get enough press, but there were 67 extra particles, new particles, which were discovered, not only the Higgs particle, at CERN in the last years, in the Large Hadron Accelerator. And then, yes, we heard in detail, there is a problem of dark matter. You heard about clumpiness, smoothness. For us, it is there a particle which is dark matter or not? That's what we would like to find out. Okay, so the science which happened at CERN played a key role in reaching these results. So CERN is somewhere between France, or includes both France and Switzerland, and the Large Hadron Collider, which is accelerating, working now, has a circumference of 27 kilometers, and that's why you see it. Here it is from an aerial point of view, and it has in it four very large detectors on top of a very complicated complex of machines, which I'm going to explain later. I'm going to discuss later. So these are 4 very large detectors which are built there, and in which these discoveries I mentioned were made. In particular, in the 2 larger ones, in ATLAS and CMS, the Higgs particle was discovered. Now here is the Director General. I took this from a slide of the Director General. These are an impressive set of numbers. to let you know what CERN is about. So I won't quote all the numbers, I just want to impress you. So look at it, and I won't test you or myself afterwards about all these numbers. Then, from the point of view of technology, there is an international collaboration which built an enormous accelerator based, LoRa, on magnets. And there are 1,232 high-tech superconducting magnets there. And indeed, there is a hope for the future that one can use these very large numbers that you mentioned, Laura, like 20 would be a very nice number if one would be able to do it on such an industrial scale. So technology there. How was this achieved from the human point of view? How did one succeed to build such an endeavor? And we heard in the lecture before, again from Bob, that it takes effort to make these things. So actually the US was deeply involved. And I don't, here is this now. Okay, here is, I can read from here now. I want you to look at the letter on the left, which was sent to Isidore Rabi at Columbia, who played a key role in building CERN. And I think this is a very important letter for the future in terms of the collaboration between the two sides of the Atlantic. So the letter says, we have just signed the agreement which constitutes the official birth of the project you fathered at Florence. Mother and child are doing well, and the doctors send you their greetings. So this project from the beginning, when signed in 1954 by 12 European states, was an international collaboration on both sides of the Atlantic. I want you also to spend a moment to appreciate, especially given the circumstance we live in now, what actually happened there. So CERN has the word nuclear in it. And while now it is doing totally different things, imagine at the time, 9 years after the war, the United States and Britain are giving to their enemies knowledge, and these enemies were fighting a bitter battle just 9 years earlier. To have such foresight that this thing is going to lead to something positive is highly commended and should be remembered. So CERN was built also in order to heal the world wounds in Europe after World War II and bring the scientists together, scientists which spent a lot of effort both to kill civilians and soldiers on each side. We have a similar project, which will be part 2, in Jordan. Now, these are a set of accelerators which were built over the years at CERN, and in which the discoveries of the W and the Z particle, the neutral currents, as well as eventually the Higgs particle were highlights, while in the United States at Fermilab, the top quark was discovered. Now, an important point which I'll need to emphasize here, there were talk about leadership, and I think at the end we have to think on a planetary scale about how leadership really works. However, when CERN was conceived, it was at best third in the world. The Soviet Union and the United States were by far leading and produced an enormous amount of great scientific results. And over the years, CERN first overcame, let's call it, in the frontier of energy. It first passed the Soviet Union, and then it passed the United States as a leading place for that. And I will come back to that and draw lessons from that for the future. Now, what were the administrative mechanisms which enabled this to happen? So CERN has two main organs. First, it has a council. The council is a council of the member states, and it decides It's not there just to observe. It decides what the scientific and financial policy is. Once that is determined, the Director General, with, in this case, her group, need to execute these ideas. And, of course, the Director General also supplies the Council with the input on the basis of which the Council can decide what is doable and what is not doable. So this is the governance structure. On the red team is the Council, and on the other side is the management with the Director General. So, as I said, the CERN Council, and you get here one picture of it, is the decision-making authority. It constitutes nowadays of 23 member states. Each member state has one vote. It doesn't matter what financial contribution they give, which is a very challenging way to administrate such an organization. I won't enter here into more details. There are small letters in the contract which were written over the years. Then there are several associate member states, there are several observer states. The United States is one of the observer states for many years. Now, the laboratory is a laboratory. It's the leading laboratory in the world, and it has people, scientists from all around the world, which play a key role. Without them, of course, this would not work. And you can see here in more detail the total amount of participants, and you see that, for example, from observers states, there are almost 3,000 participants, and actually the US group is the largest group of participants at scientists and engineers which participate in the experiment. The member states overall are more, but country by country, they are less. Also, the Russian Federation group is very large. What about younger generation? Laura again emphasized the importance of education of younger generation. So you see that the age is peaked right now around 27, so it's a young field. Lots of young people working, and from the point of view of society, they afterwards go, not of course only to academia, but they enrich the industry potential in the countries from which they come. Now, CERN right now has a plan till 2041. It has a plan, first of all, to extract whatever is possible out of the Large Hadron Collider, and then from 2029, there is an upgrade which will allow, by increasing the luminosity, provide a program till 2041. In particular, it will allow increasing the cross-section, which is, you saw from Bob's picture how the more data you have, the higher resolution you can have. So in our field, the more data is, the higher precision you have. And by increasing from the order of 100 or 200 inverse femtobarns, which is a measure of the cross-section, one will go hopefully to up to 3,000. So this is the near-term future. But what about the larger future? So here you have to bring people together, and I like to quote here from Churchill, who says, why you may take the most gallant sailor, the most intrepid airman, and the most audacious soldier, put them at a table together, what do you get? The sum of all fears. And you may not expect that, but it's true. So what about us? So here I would say, from my experience, well, put together the most enlightened governmental official. Is there someone here? A governmental official? Okay. The most creative accelerator engineer, the most inventive high-energy experimentalist, and the most brilliant high-energy theoretical physicist. And what you get is the sum of all their fears, but you also get the sense of their dreams. And I think you heard a little from Bob. You could smell the sense of their dreams. Okay, so how to go further. What's the way? So one way is national. Okay, you can hear, yes, nationally, this is very good when you discuss with your authorities. We want to continue to establish leaderships and so on. So we go on nationally. The other is internationally. Of course, then there is a global thing, which would be a very lofty ideal, but right now doesn't seem achievable. So CERN is an example of an international, or truly, I think, international organization. CERN and the US, as I showed you, had a long history from the birth. And maybe it's good to emphasize here also the other part, because now you can get memoirs of the State Department, where the State Department laments a little bit that up till now everybody spoke only why scientifically one wanted to build CERN, but it was part of a vision included in the Marshall Plan, so it wasn't an accident that actually this organization was formed, and it reflected joint interests of the United States and Europe. Also, it said that Rabi said, well, it is to preserve the International Fellowship of Science, and also to allow American physicists, if they come to visit Europe, to have someone to talk to. So I think at least this has now been achieved. When they visit Europe, they have someone to talk to. Okay, so what does CERN have, which is why I think each international collaboration should have a strong CERN component in it? Well, it has stability in funding. Over 25 years, I took those, one could go back from the beginning. Around 30 billion Swiss francs, which today is like dollars, were invested. This, by the way, is what is projected for the next 25 or 30 years that is needed in the field, if it will have a vision of a certain kind. So this has been done, and it has been done year by year on a fixed budget, 100% paid. And if you consider the history of the 23 member states and follow it, and see that they succeeded all to stand up to their obligations, even though things went up and down, that's amazing. So from the point of view to assume, let's call it leadership, there is the will to put money on the table. There have been at CERN a large number of discoveries. I mentioned a few of them, and there has been an amazing progress in accelerator technology. Okay, so this we have been. On top of it, and that I think is maybe a key component, it was that at CERN, the knowledge, the technology that is human and hardware were always concentrated in the same place. One didn't have to go from Brookhaven to Fermilab to Texas. One concentrated everything in one place, and I think that actually helped. And I see it when you see the amount of knowledge that sits in the place. It played a key role in what CERN has become. And of course, it has for it that people are coming, scientists are coming from all over the globe to work there. So in deciding to do what to do next, you realize that now, in a way, being for the first time the one which needs to provide leadership in the field, it's also a lot of responsibility. How do you do it? So the decision was to take a bottom-up approach, a process similar to what the high-energy physics community does in the US under the name of SNOMAS. There were three times in which a European strategy group for particle physics was formed, and the difference in years was about 7 years between each case. And the approach was bottom-up. It started by asking the community what you want to do, because you realize if you build the most fancy stadium and no athlete wants to compete in this stadium, you didn't do anything. So you need to ask what the community wants to do. Especially that one goes into this type of projects, the people which want to do things will dedicate tens of years of their life for that. So it's an enormous task to take upon yourself. So it's really important to know what the community wants. Then we have a process where already the funding agencies are involved together with the scientists on deciding what is going to be the suggestion of the community to the CERN Council, and then it goes to the CERN Council. The first 2 times it happened, it was a non-brainer. The first time, the first thing to do was to complete the LHC. Okay, that's obvious. The second time, the decision was do everything possible with the LHC. But the third time when we met, this was in Bad Honnef in 2020, in January, just before the outbreak of COVID-19 was realized, it wasn't anymore obvious exactly what to do. So the studying of the properties in more detail of the particle, which is just being discovered, the Higgs particle, was on the agenda of everyone. But more, I give you here a typical council meeting, and I show you what's in the head of the various people as they think about the future. Okay, so if I go in Hebrew from right to left. So the first person, this is going to cost so much money, from where would we ever find it? Person number 2 is in a deep angst, to be or not to be. Namely, she asks herself, okay, up till now, we knew that we are in a win-win situation. Namely, that either we are going to discover that something is there, or that we will discover that something else behaves as if the particle that we think is there. But from now on, we don't really know what's going to be there. We have no idea what's going to happen when you scatter quarks, not at 1 TeV, but at 10 TeV with each other. So it's unknown, and you begin to discuss issues of precision. So will agencies care if a certain number, 11 digits, is 1 or 2? It's not an easy issue to look at, even though you are touching upon the most fundamental things about the structure of nature. Then, of course, there is the one who wants to find the particle. This is a resonance, and that would get the headlines that the funding agencies want. Then there are others which think when you talk about the magnets, maybe this will change the train system in the world. If you succeed finally to have magnets which can be applied in this case, maybe even the US will suddenly have a train system of that nature. And there are those which think of the contracts that they may get to dig the tunnel, because you need a 100-kilometer tunnel. What are the options? The options available in a very simple language are a point, a line, or a circle, or something new, because one always wants something new. So the point means keep the tunnel as is and improve the magnets. The line means build a linear collider to study the properties of the Higgs. A circle means build a 100-kilometer collider in which you may study the properties of the Higgs and afterwards also other particles. So here you see the pictures, both of the design of, it's called the Future Circular Collider. I wish that one day we move the future. It has to be changed by something else. You can't keep on building a future collider. And below it, you see a design which is not accidentally very similar for an electron-positron collider in China. Now, these are the estimate timelines and costs. So again, I don't ask you to look in every detail, but I want you just to absorb the magnitude. So from the point of view of time, these are large time scales. From the point of view of cost, as I told you, it's comparable to the investment which was already done in the field, but these are the facts of it. Now, the spirit, when you face such a problem, I was always inspired by the American frontier movies, okay? And here is Bjorken, a very well-known US scientist who left SLAC on the West Coast, went to Fermilab when the issue was how to think of the new accelerator, and he didn't think small. He thought of an accelerator of 1,000 TeV. Okay, now we are thinking of a 100 TeV machine. This is, I want to show the amazing success in discovering the properties of the Higgs, which was an unbelievable experimental achievement. These are the data for first an electron-positron machine sitting in this 91.2 kilometer tunnel, which if it will be excavated, then we come to the 100 tera-electron volt hadron machine. This is a line machine. It goes on one side of the lake. Now, Council was united in the idea, in the decision to be able, the CERN should continue to be able to offer the best facility, both technologically and from the point of view of the interest it offers to the community of experimental high-energy physicists. This all 23 member states agree on. What they don't agree yet is on the vision to achieve it. So choosing between the lines, the circle, and the point is still a challenge. What Council was able to agree upon was to charge management of CERN to build a 5-year feasibility study of a circular collider. So this was given, in a way, the first chance. Is this feasible? Sustainability, environmental, and technologically. And here one depends a lot on the magnets. I'm afraid that some things that Fabiola said in 2019, she was a little too optimistic, and there are some difficulties on the way. It's a big challenge. I'm showing you this related a little to the question Bob was asked about Hawaii, because these are all the different communes in France and in Switzerland, which right now CERN management is negotiating on the future program. Each of these, their life will be disturbed, but there will be more income available, more job opportunities for the people living there. But enormous amounts of earth will be extracted there, and one needs the agreement of all of them. So on the one hand, it shows you how difficult it is to do, but on the other hand, it shows you how serious one is, because these negotiations are happening with each commune. Now for the future, collaboration or competition, where should we stand? I believe that one has to find, in the next step of our evolution, a way to have both together and have it collaboration and competition together. Competition is essential. We are all strong individuals, but these tasks cannot be achieved by one person. So again, maybe a better word will be found. So I suggested 2 words, but they don't go smoothly. So maybe somebody will find a smoother, these look clumpy. Maybe somebody will find something smoother to do that. And I hope very much that just like CERN succeeded to be the jewel in the crown of Europe and showing how you can have European collaboration, that maybe CERN will be able to show how a transatlantic collaboration could work in a way which would be a model to answer many planetary challenges we have, which need a larger effort together. So here I'm showing you a crossroad which can go either way. It depends from where you, how do you say in California, where you're coming from. So if you're coming from like this in the picture, we have crossroads. You have to decide a line or a circle. Think the other way. I'm thinking US, Europe maybe can converge into one road. Thank you for your attention.
Thank you so much for that. We have time for some questions, and then depending on how much we want to discuss, we could have fewer questions since you're giving the next presentation as well. So what questions do we have?
I don't understand the difference between a member and a collaborator and an observer, and how is that chosen? And someone explained to me why the U.S. wasn't a member, and I forgot. So could you just explain that to me?
Okay, so this is an administrative question. Okay. Okay. So it's like this. Originally, the E in CERN is for Europe. And the 12 states which originally signed in *54 the agreement for CERN were all European states. One of them, Yugoslavia, does not exist anymore, but the other 11 are there. And at that stage, the US did not think at all because it was so dominant. It did not think at all. It was nice to have someone to speak to in Europe, but it did not think that it should invest money abroad. The money was invested in Brookhaven and in Fermilab. Okay, then as the Iron Curtain fell for a while and Eastern Europe joined, this made a big change in the constitution of CERN Council. And all the Eastern European countries that wanted were accepted. And if you don't count Luxembourg, San Marino, or countries of that nature, only Ireland is not a member of CERN. And Israel, which is not to all clear that it's in Europe, to some yes, to some not, had to pass a very complicated process and become a full member of CERN. So the more or less European nature is preserved, but in principle, there is a place for geographic enlargement. So if the United States would ever decide that it wants to become a member of CERN, this will be an internal American decision. That's one issue. That was never made. And the US then presides comes as an observer. There are many observer countries, or not many, several. Japan is also an observer. This means that if you are an observer, you don't get to vote on who is the president of council, who is the director general, what is the ultimate plan that is going to be done, but you are invited to those discussions which pertain to the specific project, like the Large Hadron Collider, in which you participate. And you are invited to donate in kind to this. So this is grosso modo. There are more details, but I can continue in private.
If you don't mind, I will open your next set of slides here, and then we'll have time for more discussion at the end.
Okay, I remain the same person, but the mode of the lecture in a way changes, even though the lecture before was not a physics lecture. So here I'm going to describe something much more personal about, Joe knows that I don't like science for peace, because I think the concept of peace and just and lasting peace has led to more bloodshed than just the idea of peace. So I'm happy with understanding for the beginning. So what is different, and in what way will this talk be different than other talks? Well, one, it's going to have more transparencies. But if you don't count that, it is not based on the irrefutable logic of physics, okay? It comes, from my point of view, from inside, from our common inside. Because this is an adventure which takes place in a parallel universe. And I'm also here not as myself, but as a voice of others. And this particular thing and its relation to CERN has been deeply challenged by the Russian invasion of Ukraine. So I'm going to touch on these various aspects. So first, a voice for others. I think it's very important that you hear this if it works.
This is something I would like to leave.
How can I give a voice?
This is what I believe. It has to work because it means.
You can hold your microphone against the speaker, maybe.
Let's see, first.
So it's clipped onto your collar.
I barely hear myself.
In terms of bringing science here, in terms of bringing a line of
No,
communication.
but you need something to be able to amplify it.
It is very valuable.
You turn it up as high as you can. How do I turn it?
Okay, if it works fast, yes. Otherwise, we anyhow have lack of time. So,
Okay. Oh, you're gonna wire it in? Okay, it's connected.
okay, I give you 1 minute. If it doesn't succeed, we move on. Well, you took me out of my comfort zone. I'm not in the.
And it is very important.
Go to the
for region
beginning, then.
because we can, one country can.
Believed to next generations. This is what I believe. It has to work because it means a better.
Okay, it doesn't work. Okay,
But
so
that's okay.
I'm sorry that it's especially this. I'm told that this is the International Day of Women. I wanted to start with a very powerful statement. Yeah, but there's nothing I hear here, so it's not going to. There's nothing to amplify.
You can do it, it'll help a little bit. I think we'll be able to hear you.
This is something I would like to leave.
Okay, I think we give up. Maybe we try at the end if there's time. Let's forget it. So, this was a group of. This was a group of people coming from Palestine, from Israel, from Egypt, from Iran, from Jordan, all saying the same thing, which is very rare to hear. All of them stating, each from their point of view, why this common project interests them. And okay, now comes a question. Why is science a useful thing for a common project? So I think this is pretty clear. If you bring together two philosophers or two experts in religion, it will take them years just to find a common language. In science, at least the language is common immediately. We are not arguing Maxwell's laws. So we both accept them. And then you learn to appreciate or not the person opposite you, and you develop first the scientific knowledge of the person opposite you, which helps you, I think, pass the various barriers which we get from the media, from our education, and so on. And then we either like the person a lot personally, just like with our colleagues. Some of them we like very much, and some of them we like less, and they like us less. But science is the way to go through the barrier. And I think we get a lot from society. We're allowed to do what we are interested in. So we should give back to society. And this is what was my drive in getting involved in this. I'm a string theorist. I don't work on light sources, and this is a light source. What do you need? So if I would teach this course for understanding, Science for Understanding 101, you first need an infinite amount of optimism. If you don't have if you are less than infinity, leave the course. It's a waste of your time. Okay, I said common language. Then a lot is mentioned about science diplomacy. And here I want to make a statement which I saw very sharp when the Ukraine issue came up. For many governmental agencies, science diplomacy is another kit, it's another tool in their kit. They say, okay, it will help us further our goals. Great. When it works, it's good. If it doesn't work immediately, forget it. We don't have the budget for it. Now, in my opinion, it is important. It can be a bridge from understanding. It has been demonstrated it can be a bridge for understanding, but it's something for a long-term investment. It's not just the tool of today picked out of the kit, which is a la mode. And I saw again the fast reactions to the crisis in Ukraine showed me that this is not self-evident to the people which are using science diplomacy. Okay, if you want to do something together, there are two possibilities. You go to the government, the government tells you, with thanks to their advisors or whatever, they know what's best. They decide, they give you the budget. You like it, you apply for it. You don't like it, too bad. Then there is the bottom-up approach, where scientists come, try to convince the governmental agencies what are the important issues. And in some countries, there are people which are willing to listen. In other countries, it's more complicated, or in the same country, in different periods, it can be more complicated that happens. Now, my preference is strongly bottom-top. That's how I function. However, if you want in the Middle East, it doesn't work. It needs to have an umbrella from the top. You cannot have Arab-Israeli collaborations without endorsement at the higher level. So bottom-top is not enough. You need to have the top-bottom. Then comes the issue of small science collaboration versus big science. Now, unlike what you heard in my former lecture, as a physicist, I'm more inclined to small collaborations. Okay, again, if you want it in my region, it won't work. You need something which has presence. It has to be a big science thing. Then comes the next issue. I compromised on this, and again, I say it that people who know me know that I hate to compromise. But on this, I had no choice. I had to compromise. But there is one thing you should never compromise. It should be good science. I don't think that having collaborations where both sides don't have equal standing are very useful. You really need the situation where each side contributes and each side can benefit. And this was my experience over the years. And then I also learned that it's all personal. What Marlon Brando said according to the script in a certain movie was correct. I'm showing you a picture I like, and once you decode it, you can tell me. The next issue is about how do you form the great dreams. And first, it's good to know that somebody else already maybe dreamt them and realized them. Again, as I said, in my area, it's much more complicated. And the basic difference between CERN and Sesame is that the war in Europe in '54 was over. It was over in '45. It was clear who won and who lost. And then when you had the collaboration, the relative status in the beginning was clear. In my region, it's not clear. The narratives are different. Some people think they're on the way to victory. Others think they're on the way to victory. So to have a collaboration in such a setup is much more complicated. And then comes Ukraine. So this is an outcome. This is the place where we have a light source. It's in Jordan, El Balqa, Jordan. In this community, or at least in this APS meeting, I cannot sit and explain what light source is. Everybody knows much better than me what a light source is. I will just say here that when any charged particle is accelerated and going around the circle, it is accelerated, it emits light. And this light can be used in various manners. Unlike CERN, which is unique in the world, there are many, many light sources, but notice how sparse they are in the Middle East region. There is the one in Jordan, but look around it, you need to go a long way to find a light source. Big advantage of going for a light source in a common project in this course of ours is what are the resources in the region. CERN is very, very centered around one goal, very ambitious goal, but one goal. The basic laws of nature, the basic constituents of nature. Go get them. That's there. In our region, we don't have one subject where there's a critical mass of scientists. So a light source has an enormous advantage that it offers a large rainbow of opportunities. And here are just some. They go from, you can read an ancient papyrus which would disintegrate unless you put it in a light source and see exactly what's written in it. You can study proteins, and Nobel Prizes were awarded by such studies. You can study even physics, you can study chemistry. There are lots of interesting things, so you can build a critical mass of users in the region. Now, another outstanding thing about Sesame are the members of Sesame, and the members of Sesame include Turkey, the Greek part of Cyprus, which is not a trivial thing to collaborate on its own, Israel, Egypt, Palestinian Authority, Jordan, and Iran and Pakistan. These are not the countries which usually collaborate peacefully on anything. Now, the general objectives, which are common to all, is of course to bring to the area advanced science and evolve as much as possible the brain drain. I'll show you some photos of the journey. These are building magnets, and these are the magnets installed. How did we reach there? This I can tell you depending on how much time I have. So how much I will... Okay, so I have more than I expected. Okay, so first let's go to the dreams. So in general, beautiful dreams are rare, at least mine. Usually they're not beautiful dreams, but they also come free. And the complicated thing is to actualize them and make them real. That's where the work is. So the project itself, I think by looking just at the participant members, is very unique. There isn't any other such project in my region. We are striving to get high quality science. The scientists involved, I will show you some, are high quality scientists. And the dedication, I would say, is rather unique. Here I bring a list of Israeli scientists involved. I am here the black sheep, as I told you. I'm paid not to enter in general into labs, but definitely into a light source. I would not know what to do there. Okay, so the others know what to do and have done very good experiments and have obtained very interesting results doing that. We have also the support of Ada Yonat, who got the Nobel Prize in chemistry on working on a light source. So if we look at the index hope in the Middle East as a function of time, this is the red line, the red curve. It goes up and down, and actually it violates some theorem I learned in mathematics, I think called Rolle's theorem, that the number of ups and downs should be the same. It's clear that my feeling is that the number of downs is much larger than the number of ups. Nevertheless, on this background, we succeeded And it took over 20 years from a dream to have actually a running project in Jordan. So in this process, I remind you again, it's all personal, and I can't tell you all the personal things which happened. First, because I don't know all of them. I don't know what happened in Tehran in the offices and what were the debates there. I don't know what happened in Amman, in Cairo, or in Ramallah. I was not privy to those. But I know what happened in Israel was very complicated, and the interrelations were also very complicated. So the personal part played a key role. For me, except being born in Israel, in Jerusalem, and feeling the problem from the moment I was born, I got into this particular one by Sergio Fubini, a well-known Italian physicist who spent some time at MIT and then came back to CERN. And when he became 65, at CERN, you must retire. There's no option. So at 65, they made a celebration for him in Torino. He asked me to come there and give 2 talks. One on string theory, which I recommend to all of you to read. I think it was a very good review talk. And the second, he charged me with looking at all issues of Arab-Israeli scientific collaborations in the past. And I wrote an article on that. Actually, before he charged me, he came to me, held me over my shoulder, and said, look, it's time that maybe we look into your naive leftist ideas. And I must say I'm neither leftist. I don't think I'm very naive, but this is the way he decided to characterize me, and he sent me to do that. And I studied that, and I reached the conclusion which I already told you. In order to have a successful collaboration, you need that each side benefits from that collaboration. Then we went to Egypt actually as private entrepreneurs. If somebody wants to do, I don't see young people here, but many young people here, but I would encourage them because I know how young people today, unlike in my generation where we felt we can change the world, now the feeling is you can't make even the smallest dent in this over-constrained system, which is the world, and you try to improve your local environment, which is very legitimate, of course. But so here, as entrepreneur, backed by nobody actually, we went and met through personal connections Egyptian delegates, in particular, again, the Ministress of Higher Education, Venice Gauda. She told us that President Mubarak told her that she can take politics out of scientific collaboration, and therefore she's free. So we sat, this is early Macintosh thing, which was in the Italian embassy in Cairo. We wrote down an agreement. Again, Sergio signed in his name, some invented committee at that stage. I signed as chairman of the department, which I was at the time, but does not exactly give you the status for diplomatic collaboration. But the Egyptians signed on an official level. As a result, we had the first and last visit of Egyptian scientists to the Hebrew University in Jerusalem. You know that the Hebrew University got, by inheritance from Einstein, a lot of rights. So I think that Albert Einstein, looking at us, is approving of this meeting. And the result of this meeting brought us, okay, I'll tell you a few anecdotes. So that's one interesting anecdote. It brought us to an issue which is very sharp. Per diem. The Egyptians came to visit us. How will we pay them? I can't pay for them for my string research grant. This is not what it's about. So Sergio Fubini, I remember in a gesture, took out, I don't know where he had it, a checkbook, and said, I'll sign a check. I told him, you are welcome. My Israeli salary does not allow me to sign such a check, and our endeavor will go nowhere if it lives on these checks. So what we did, we called Miguel Virasoro, who was head of ICTP, which was mentioned before, and who was a friend and also a leader in the field of high energy physics. And he said, what do you want? We said, we want some money. He said, okay. And he wrote a letter. It's very important to get it in writing. So he gave us the money so we could seed money so we could do the process. So without ICTP, it wouldn't have gone. Then we made a meeting in Egypt, and the idealism was really there at a very high level. If you look at what's written there, you see the word physics in Arabic, in Hebrew, in Italian, and in English. And if you look at the sponsors of the meeting, they are very rare. They do, usually University of Bethlehem and Hebrew University don't sit together on projects. And you see from Cairo and from Amman. And we had outstanding scientists there as well. We had it, if you wish, in a Bedouin tent. So we had all the kitsch. We are not far from Hollywood here. So we had a red tent. You see me here because I asked to take a photograph of me, so someone took that. And but next to me sits Gwenis Gauda, the Ministress of Education, and she started this meeting by asking us all to stand to honor Yitzhak Rabin, who was murdered by an Israeli 3 weeks earlier. So to have 100 Egyptian scientists, including from El Azhar University, standing for Yitzhak was a moment one cannot forget. We also had an earthquake of magnitude 7, and people in the Sinai were killed around us, but not at our place. And to top it off, there was a group which visited Mount Sinai and saw it shake. So I think you agree that we got all the signs that something is going on here. We signed an agreement. However, we could not fulfill that agreement. We already had a next school, which was leading climatologists to discuss the El Nino effect. We couldn't do it because politics came back into science due to deterioration in the region, and we retreated without dignity back to Torino. In Torino, for the first time, Gus Voss suggested to us not only to collaborate in high energy physics, but also to collaborate in light sources. So we discussed that, and this idea was of his and of Herman Winnick, and I will come back to it. So we had, just to know, we live in Israel not in houses, but we live in apartment buildings, and I had neighbors, and the neighbors used to put clippings from the newspapers in my box asking me, do you know what the hell you're doing, or are you doing the right thing? So this is Herman Winnick and Gus Voss here, out of all places in Armenia, which is another story I won't tell you today about. Okay, then we needed to go ahead and construct the foundations. Why to choose a light source, I explained to you. That makes most sense. At that stage, Herwig Schopper, who was a past DG of CERN, was recruited to join us. And Fubini was slowly stepping out, and Herwig took together with him, he recruited Khaled Toukan from Jordan, who played a key role in what happened later in making Sesame a reality. So they came with the following idea. There is an old machine which is going to be junked in Germany called Bessie. Why don't we take it? So if you're good students of my course, I think you know what the answer is after I indoctrinated you that you don't compromise on quality. Would you take a machine which be junked? Who will come to work there? Nobody will come to work there. Okay, so we took it. Why did we take it? Because you need to build an administrative construct when you have countries which have no relations between them, most of them, and even when they have relations, they are tenacious. They are very tenacious. So we did take it. We met in UNESCO in 1999, and we decided to actually form Sesame. The question was, where would we have this light source? And there was a big discussion about that. I won't enter into the details. There were lots of candidates, and the final choice was to have it in Jordan. Before that, on March 2000, I visited Amman. I got the clearance half an hour before the airplane left because of security issues. I met Khaled Toukan in this hotel, and we discussed where is the best place to have this machine. And we decided that it's in El Balka in Jordan. And the Israeli request, which now sounds like science fiction, we said, Israel puts to you one condition. We want a Palestinian to be Director General of this endeavor, of the project. And Khaled Toukan said yes. Unfortunately, for reasons I won't discuss here, this never happened, but it was for irrelevant reasons that happened. In any case, these are the early suggestions where to hold the place, and indeed there it was held. This are the initial program. So again, for the younger people, I want to show this. You see, this is something also Bob showed you, okay? This is something which is a dream, okay? It's a stage of a dream, but eventually this became real. Many of these things don't become real. They remain like that. But this one became real. Then at CERN, on the 11th of April, we decided that Jordan will be indeed the site. Then we took the German machine in a very complicated manner. This is some of the physics I'm doing, but I spare you that. In a project in which Russians from Novosibirsk with Japanese money went to Berlin, took the machine, put it on a ship, sent it to Jordan, and most of it is still there in Lego boxes. However, it gave us a structure. In 2003, we were able to have the place inaugurated. These are the original suggestions to the place. Then it gets built up. Here there's no voices, so you can just see the way that an Israeli would do, going through Jordan, going through the West Bank, then Jordan, and then going to the place. That's the place itself. 2008, inaugurated. That put, I don't know if you heard of holography. I won't explain it here, but it says that if you know what the boundary is, then you know what's inside the bulk. So that's when you see someone and you say, you look great, so you make the assumption that what you see here is what's inside. Okay, it doesn't always work, but in string theory, there are concrete cases where it works. So here is the machine, but it's empty, because there was money to build, but there was not money for the thing to build something inside. Here, another Director General of CERN, Sir Chris Llewellyn-Smith, took over the presidency in a friendly manner. We had all of our presidents of council were Director Generals of CERN. This is apropos the high quality of scientists involved. He had Nobel laureates visiting the place and asking for support. The place was empty, so what we needed to do is fill it with something. So it's easy to fill it with shielding. There's nothing to shield from because there's no machine, but at least if there would be a machine, it's shielded, so it looks full. There were some singularities here and there. I'm not going to discuss them. We filled it more, and then eventually we took a move. We went, I see that I'm reaching the end, I'll speed up. We went, Israel took an initiative. Here was an Israeli initiative, and we suggested that some countries give 5 million each in order to push the project to success. This is a meeting. You're not Israeli, so you don't realize how significant this meeting is, because it has in here 2 members of the finance ministry, which are usually the enemies of the professors. So we are sitting here together and asking for that Israel give the 5 million. Israel gave it under the conditions that other countries would give it. Other countries gave it. On the 10th of March 2012, we met in a small room in Amman. Iran, Israel, Turkey, and Jordan each pledged to give 5 million in order to boost the project. And here was sitting ex officio the Palestinians, Professor Salman Salman, and the Egyptian Yasser. Okay, then we got from Italy 5 million to move the project forward. Then finally Europe was willing to give the money, and we could push the project and make it real. And this, with this money on a shoestring budget, on this date, we were able to officially inaugurate. I'm showing you here Edward Witten, which you may recognize, who came there to see this special moment, and to show you the high interest. You don't recognize in the US probably this person. His name is Carlos Moedas. He was in the government of Europe, or European Union, he was the Minister of Research. And he came there as well because Europe gave a lot of money. A lot of good things happened to the region from that. You should have asked me, why do I show you both blue and gray photos? So it looks like photoshopping, but it wasn't. We had in 2013 the biggest snowstorm ever that the elders of Jordan don't remember, and the roof crashed from the snow, but it was of no significance because there was nothing inside except the shielding. So we passed one more test. These are the 3 beamlines which are in operation now. There is a 4th, very modern one. These are pictures from December, which are being constructed there. So this is now a reality. It's not anymore a dream. There are papers coming out, there are publications, 64 published papers, some of them in very good journals. People are working on problems which are relevant to the region. The slogan, which I think is correct, is that the scientists in their drive broke boundaries and took the project and their countries to where no one had the right to expect. And once it happened, for some reason which I don't understand till today, the politicians did not blink. They accepted it. Now comes the issue of preaching, which I must go through, because it's relevant to the US also nowadays. But it was relevant at the time in Europe. I used it first in Europe. That you could read in any newspaper exactly what the Arabs should do and what the Israelis should do, what the Palestinians should do. Everybody knows in great detail every small thing which exactly everybody else should do. But then when you have a project which works, somehow it doesn't follow within the appropriate budget structure. And this, to me, was very disappointing, because this is something real which happens. And when we ask for help, for a long time was not given. Finally, Italy and the European Union made a big change and gave a lot of money to the project. Here are some money. Israelis, which was for me a big dream, made experiments in Jordan, experiments which were published. This is the group of Israelis doing it. I already talked about the high level, and we are the first green accelerator. We have a solar plant, and we provide our own energy, which is very useful in the time when the energy costs are so high. Then Fubini got, out of the Italian money, we built a guest house, and it was dedicated, these are all Italians around me, the Italian ambassador in Jordan, and the heads of INFM, the former, Nando Ferroni and Antonio Zoccoli, the present, which all were there when this guest house was dedicated to Sergio Fubini. In the US, we visited OSTP once under Obama. We visited OSTP twice under Trump. Actually, under Trump, the reception was more, I must say, surprisingly to me, but was more, let's say, coming forth, but nothing happened. Then we had Bill Foster, the congressman from Illinois, whom we met and who is trying and succeeded twice to pass through the House of Representatives a bill of the US for Sesame, but when the agreement with the Senate had to be reached, this fell. So we are in a situation, I think there is another now more general declaration about intent, and we are waiting to see what's going to happen. For me, it's very disappointing that the US, which is so heavily invested in the region, doesn't find a way to support such a positive thing. Here, for me, something personal, very special, which I don't see happening elsewhere. This was in July in Ankara. in the time when in the newspapers was says that Iranians were trying in some retaliation to kill Israelis in Ankara. So I was there, and here, because Rolf Hoyer, the current president, had COVID the night, or detected his COVID the night before, I conducted the meeting. So I'm conducting here, I'm as vice president, I was given the chair. I conducted the meeting there with the Palestinians, Iranians, Jordanians, United Arab Emirates, Egyptians. Nobody left. Everybody stayed a full day to discuss the issues that we had in common. Okay, for those who think there was a lot of tourism, this is the reality. And it is a tough region, but there is a little bit of hope. My epilogue. What happens now at CERN? Well, we have a situation where Russia, an observer at CERN, invaded an associate member of CERN, Ukraine. And Europe demanded a very strong response, saying that it's impossible to collaborate in such a situation. And they requested the dismantling of bridges, and the emotions were understandably very high. To me, it was a little strange to see this, because people used to pat us on the back for Sesame. And now, when faced with a similar situation, you suddenly see that they don't react like that. Okay, but here I end, and this is my last statement, is some of you, I'm sure, are parents. And one of the moments in parenthood, you discover that your kids can be smarter than you. Okay? It's not easy to accept. And sometimes you find that, okay, there are areas, let's say, which are smarter, that you can find ways to live with it. There are areas where they understand the problem better than you understand them. You understand the problem. So from this point of view, if we look at CERN as Tarzan, and we look at Sesame as the son of Tarzan, maybe in this case, a little bit can be learned also from Sesame. And for me, it was easy when I talked to ambassadors of European countries to tell, you can't tell me you can't talk with your enemy. I'm talking with my enemies. You can't tell me it's impossible. There are ways to do that, and it's important for the future. So that's one lesson, and I end by showing you a letter which we were very proud to get when the issue reached the CERN Council about how to react to what CERN responds to the Russian invasion of Ukraine. We got a letter from all living director generals of CERN in the past, and they all brought us as an example Sesame, telling us that we should learn from them. And I thought that's nice to hear. Thank you.
Thank you so much for that incredible talk. I think we have time for maybe one quick question while I get the next talk set up.
I wanted to follow up on your comment about getting the old equipment, Bessie 1. So I think what your fear has sort of been realized recently because, as you mentioned, Sesame is looking for a new injector now. The problem is not so much that the old material equipment broke, but it's the technology, is not up to date. So that's another bad side of getting old equipment. The technology is not going up to date.
I think experience is that it's better usually to buy new equipment than to have to refurbish and adjust various pieces of old equipment. So it's very nice to get lots of contribution of old equipment, but it doesn't form a firm basis for the future. So the machine is new, and what we took actually from Bessie is just one thing, a piece of metal, in the beginning, as you said, in the beginning, so the microtron, and also CERN, the LHC, has as its beginner a 60-year-old magnet, and that's okay, you can live with it. The problem is that if that injector will fall, there's nobody who knows how to fix it. And then the machine is done. So yes, we are looking from the United States to help in having this Achilles. This is our Achilles heel, that part, and it would be of great help if we
There's
could
a
get.
small group, actually I'm a part of that, who has been trying to talk to government officials in the U.S. In fact, during the AAAS meeting last week, we had a chance to visit with various governmental officials to just explain the situation. So, in fact, on Monday there was a meeting with Bill Foster's staff. He wasn't there; he was out of town. But we did have a chance to talk to his staff, his senior staff. So there is a movement to try to do something about the injector there.
Okay, I hope that this general thing which was passed through Congress can be targeted to Sesame and not remain too general and not used.
Yes.
Thank you for your help.
See if I could.
What's going on?
I know. I'll just see if I could bring up the volume, but I guess since we're over here.
Yeah, but I'm just concerned it's not showing your file. Is that where your file was?
Yeah, it should be. I loaded it. It's not showing from there.
My files?
No file has been uploaded.
Okay, well, let me give.
Is it 3 o'clock?
Is it this? There we go.
No, that's
That
Laura
okay.
Green.
And how did that one get? Didn't we just have it up before?
Yeah, we were looking at it right before the. I can go and get my flash
Oh,
drive.
wait. 3 o'clock, maybe?
No,
Is that 11?
it's this session. That's him. Yeah. Yeah.
I checked it just before.
I feel a little bit like I'm taking crazy pills. Well, thank you for being so prepared.
So I.
As we get that set up, we're welcoming Sikazi Mtungwa. He is a theoretical high-energy physicist and a founder of the African Laser Center. He is a co-recipient of the 2017 Robert Wilson Prize for Achievement in the Physics of Particle Accelerators. He was elected a Fellow of the American Physical Society in 2008 and also co-founded the National Society of Black Physicists in 1977. And he served in various other national and international initiatives. So please join me in welcoming him, and hopefully it's working.
Do I use that?
You can use that.
Oh, here we go.
Does it work?
Lavalier is working. This one is off.
Okay, so that's working. Okay, so then I need to go back to, does it go here? Okay, great, fantastic. Okay, thank you. Sorry that we had that difficulty. So I'd like to talk to you today about two projects that I've been involved in. One is the attempt to convince African governments to pool their resources and to construct an African light source synchrotron facility somewhere on the continent. And the other one is a project called LAMP, which is the acronym for Light Sources for Africa, the Americas, Asia, Middle East, and Pacific. So basically the whole world, but it kind of grew in little small pieces. So we've had to add some A's as the organization has progressed. I don't get it. Something's okay. Okay, so advanced light sources. You've seen a map like this that shows the positions of these advanced light sources, which include synchrotrons as well as free electron lasers. And the important thing from our work is that Africa is the only continent in the world besides Antarctica that does not have a light source. So basically, it's the only habitable continent that does not have one. And so we are trying to address that. And I'd like to point out that our deputy chair of the African Light Source, Professor Prosper Ngabanziza, raise your hand, Prosper, who is sitting right out here. So I hope I don't make any mistakes. He can, set me straight if I make a mistake. And he's from Rwanda, by the way, although he's currently a professor at LSU. He just recently moved to LSU. So these light sources, let me just say a few words about it. Just like Professor Rabinovich, I'm not a light source user. I don't know all the details, but I only know the big picture of what a light source is all about. So this is the only light source in Latin America. This is the Sirius light source that's located in Brazil. And for the schematic of a light source, it's just a pointer here. Okay. Okay, so you have on the right, you can see that there's some electron gun, some source of the electron beam, and it's accelerated down a LINAC, a linear accelerator, up to a certain energy, and then it goes into this small ring called a booster ring, where you can kick the energy up to whatever it is finally you want to use, and that is injected into the big ring. And you can see all these little beam lines that are coming off of this. Now, this schematic is from the advanced light source, the APS at Argonne. But the point is that you can have anywhere 50 to 100 beam lines. So the thing that excites me about these light sources is the fact that you can have so many experiments and so many fields going on at the same time. I was a young scientist at Argonne when this thing was being built. Okay, I was doing, at that time, something called plasma wake-field acceleration. I had kind of, thing about working at Fermilab before that, I sort of made a transition from only doing theory to doing experimental work. So I was getting my hands into this field of plasma wake-field accelerator. In fact, our group was the first group to demonstrate this principle. And I just started thinking in those days, this is something that would be great for Africa. So that was sort of in my mind back in around 1990, it was. Okay, but anyway, the electron goes around this circular accelerator, but it's not really an ideal circle. If you can imagine going around, having an electron beam that's going around, every time it hits a dipole magnet, it gets kicked. And it goes this way straight, that's called a straight section. Next dipole that goes through, it gets kicked. And every time it gets kicked, that's when the acceleration takes place. And it throws off the radiation, okay? But then, okay, so that, eventually people decided, hey, I can do something even better. In addition to kicking the beam, throwing off the synchrotron radiation, I can put what we call insertion devices along these straight sections. And these insertion devices can wiggle the beam, and that causes intense, in fact, even brighter beams of X-rays that can come off of that. So you have all of these things going on. So some of these beam lines are from the actual magnet kicking the beam, and others are from the insertion devices. And this gives you a schematic of a typical insertion device. These things have called wigglers and undulators. They basically are these alternating poles. So you can see the electron beam is coming from that side, going through here, and it's wiggling through there. Now, the only difference between the undulators and the wigglers, the undulators, the electron beam is making wide excursions in this direction as it wiggles through. The undulator beam makes very little undulations like that, and that causes a much brighter beam. So the brightest beams come from the undulators, and the wigglers and the magnets, dipole magnets, are not quite so bright, but they all have different applications for the scientists. And to give you some idea of an undulator, here's a man who's, I guess, he is on the order of, between my height and somebody else's height. Well, he's not an ant. So to give you some idea of the length of these undulators. So the beauty of these synchrotron light sources is just as I stated. You can see people are doing biology. Right, during the COVID pandemic, a lot of the information about the molecules that make up the coronavirus, the structural biology of that virus was deciphered at these synchrotron light source facilities. And you can see material science, even paleontology. That's a real big thing in Africa because there's a lot of paleontology going on all over the continent. And much of that work is done by synchrotron light sources. Okay, so that's sort of the general idea of these synchrotron light sources. I'm going to talk about the African light source, but the important thing, before you build a light source, you have to have people who know how to use them. So our big challenge has been training people. That's not only the case for Africa, but that's for these other regions, like the LAMP project, Africa, the Americas. And when we say Americas, we mean Mexico and the greater Caribbean region. Asia, we mean Southeast Asia, and Middle East and Pacific Islands. So these are the members of our executive committee. The woman to the left of me is Marielle Akbahumbata from Benin, and I'll say something about her great work that she's doing, training researchers and students in crystallography. And Özgür Öztürk, who is in Germany, University of Siegen in Germany, she's a big light source user. She does even synchrotrons, and she does X-ray free electron lasers. And then down on the left, far left, is Sandro Scandalo, who is like the top, next to the top official at the International Center, Abdus Salam International Center for Theoretical Physics. And then there's Michele Zema, who is at the University of Pavia, but he also has been a big official with the International Union of Crystallography. So we have a great team, very small team, but we meet quite often, and I think we get quite a bit done. Okay, so for the LAMP project, we have light sources that are who are partnering with us, and you can see there are 17 that we have now, and these are light sources who have agreed to train people in one of our programs where we send people to the light source for 2 months, and they provide housing and other types of assistance for them. Because the nice thing about light sources, in addition to the fact that you have all of these fields going on, once you go there and get trained, you can go back to your home institution and you can actually prepare samples and mail them in. And then the staff scientists at the facilities will insert them in the beam lines, and you can collect data. So that's another great thing about these light sources. They're really just revolutionizing the way that we do science. Okay, so for LAMP, we have 4 main tasks that we enumerated when we formed. One is to develop the strategic plans for each of those regions. So we did do that. There's another program called the Colloquium Program, where we send experienced light source users to these various regions of the world so that they can spread the good news about light sources and try to engender interest for people to want to get more information and more training in how to use them. The task 3 that we had, we have a brochure that we've produced for the layperson So if you want to learn about light sources, if you're not familiar with them, or you have children at home, who would like to learn about light sources, give them one of our brochures because it explains everything from beginning to end, what these light sources are all about. We have them online. I have a few copies there, actually, and it's in 5 different languages. And then the biggest project that we have is this FAST team project, where we send people to light sources for 2 months of training. So for task 1, we have the strategic plans, colloquium program. In fact, the gentleman in the middle there is the same gentleman that's sitting there, Prosper Ngabonziza, who went back to his home country of Rwanda. And you can see this happen right before the pandemic. We were trying to get this all up and going again, but most of the activity in terms of visiting was done before the pandemic hit. The gentleman on the left from Argentina did some lectures in Central America. And on the far right, we have one of our friends, Thierry Dalmeida from the French Atomic Energy Commission, who is from Benin, and I will just say, when he went to Benin, what he discussed was so impressive to the president there that they invited him back. And he was able to come back and to meet with the president's cabinet, which you see in the photo there. And they established this laboratory. It's amazing. This laboratory, X-Tech Lab, that they established, has been extremely active in training people in the art of crystallography. And what we try, we try to have 2 sessions per year for 2 weeks each time. And over the years, since 2019, over the years sounds like a real long time, but since 2019, we've trained, it's even far more than 84 learners now. But you can see that not only Benin, but they've been open to train students and young researchers from many other African countries. And we've had a lot of experts. I'm just so impressed with people who are willing to come and, in-person lectures, to come and give lectures and to really excite the students about the art of crystallography, which is very important for light source users, right? Preparing samples. Okay, task 3, the brochure that I mentioned, there's the website for it. And as I said, it's in French, Spanish, Portuguese, Arabic. Much of this is coming out of Italy, but it's not in Italian. So maybe Joe Nemila can get somebody to translate it into Italian. Okay, but the faculty-student team, as I said, this is our most intense work that we've done, where we send a faculty and a student, graduate student, to a light source for 2 months of training. And this was the case for Phil Oladijo, who's in the yellow shirt there from the Botswana University of Science and Technology. It went to the Synchrotron Light Research Institute in Thailand. In fact, he went twice. We try to send people back the following year. And you don't have to go back to the same light source. He went to Japan, actually, before he went to Thailand. Okay, so then now let's go and turn over to the African light source. So here, this has been a big effort. People like to say Sesima's 20 years, right, from your initial meetings. We've been 20 years now from initially talking about this to even where we are now, and we don't really have the commitment. So, wow, this is sort of a long process, and that's one of the downsides about the accelerator field. It just takes a long time. But now we're going to have our conceptual design report coming out in the very near future, hopefully in about another month. I'm the lead editor for it, and unfortunately I've been doing so much travel and all. I was hoping to have this done in January, but it didn't work out. Then I said it February. That didn't work out. I won't even say March now. I will say April and hope for the best. With your prayers, maybe I can get this. We're down to the last chapter. Okay, so the conceptual design report, as I said, is not so much on the technical side of the machine, because these light sources are very well known now, right? And the sweet spot is 3 GeV and 1.5 GeV. Max 4 in Sweden was the first to construct one of these so-called fourth generation light sources using this technique, this technology called multi-bend acromass. That's just the number of magnets that do that bending of the beam. And it turns out that you can get a much smaller beam by bending more times. Instead of taking a big bend, take small bends. And so the technology is well known. So the idea for this conceptual design report is to explain as best we can to governmental officials what this light source can do for the social economy of the countries. So we talk about what a light source is from the very beginning, what is the electromagnetic spectrum, and so forth. And then in chapter 2, we spend time talking about the scientific benefits, like structural biology, fighting infectious diseases that are prevalent in Africa. One of the advantages of having a light source in Africa is that it can tune the priorities of the light source to address its own problems. Sure, scientists from Africa can go to other light sources in other countries, but there you have to bend to whatever the priorities are there. But if you have one in Africa, you can devote it to those diseases that are really just ravaging Africa. Then we talk about the materials applications for energy, materials for energy applications, solar energy, fuel cells, various batteries, understanding geoscience. Mining is extremely important for Africa's economy. And environmental science, plant, soil, agriculture, paleontology, as I've mentioned also. And this is a map. The little dots show you where samples have been taken for paleontological studies at light sources. The big squares have to do with more of the minerals that you generally think about. But you can see all over Africa the little dots, how paleontology could really make a big use of these light sources. And then chapter 3, we turn to socioeconomic benefits, although even in the scientific part, you can see the benefits because of the work on the coronavirus and so forth. But, disease prevention, food security, improving packaging, for instance, clean energy, as I've mentioned, and just the sheer economic benefits to the host country. And here's a quote that I like to use from Andrew Harrison, who's the former CEO at the Diamond Light Source, where he says for every English pound that goes into the facility, 3.5 pounds come back into the economy of the UK. So, there's money that comes out of this. So the economic and social benefits are extremely high by having these having these light sources. Okay. Forgive me for the vertical timeline. But it shows in the 1990s, the first users of light sources were in Egypt and in South Africa. It was in 2001, 2002, that we made the first call for a Pan-African light source. And this came from an organization that I was involved in. We founded in South Africa called the African Laser Center. And the African Laser Center exists even to this day. I mean, we're still giving many scholarships to students and to work in laser laboratories for their master's and PhD theses. We give grants trying to form collaborations between African researchers and researchers, South African researchers and researchers in other parts of Africa. It's mainly funded by South Africa, so we have to, have in every one of these grants a South African researcher involved. But we give these grants out every year. But anyway, way back in 2002, we stressed the importance of bringing a synchrotron facility to the continent. And it was not really until 2015 that things really sort of took off. And we held a conference that we were invited by Francesco Sette, who is the Director General of the ESRF, the European Synchrotron Radiation Facility. And it was there that we actually formalized a governing group, which became the African Light Source Foundation as a nonprofit in the country of South Africa. And then since then, we've had about, how many, Prosper? About 5 conferences, although a couple of them may have been virtual because of the coronavirus. And we also had when we were in 2019 in Ghana, the president of Ghana, said that he would champion this to other heads of state. And this is a picture of the participants in the ESRF, the first African Light Source Conference. And then we have the African calling stick to convene the conference. I guess I'm holding it, but I'm not so important. The gentleman to the left of me is Simon Connell, who's a professor at the University of Johannesburg in South Africa, and he has served as the chair of the African Light Source Foundation from the very beginning. I started as deputy chair, but it occurred to me more and more, we need to have someone, since I'm from the US, we need to have people from Africa. Now, Prosper took over, but then he moved to the US. But he's still from Rwanda, so you're forgiven, Prosper. Okay, so one of the things we did at that 2015 conference, we gave the why for an African light source. And you can read through these. The first one, advanced light sources are the most transformative scientific instruments, similar to the invention of the conventional lasers and computers. In other words, cutting across so many different fields that it contributes to. Advanced light sources are revolutionizing disciplines in applied and so forth, many in sustainable industry. The community of users around the world are striving collaboratively to construct ever more intense sources of these. So you can see we're going through these generations of synchrotron facilities. We're now at the 4th generation. I don't know when the 5th will come, but Africa has to get involved in this, otherwise we will just be left behind, and so forth. So we articulated the whys, and as I mentioned, the president of Ghana, President Akufo-Addo, said that he would champion this among his other head of state colleagues. Okay, so that was chapter 4, dealing with those issues of history and so forth. And then chapter 5 of the CDR, we're going to talk about the history in more detail and capacity building, like how the ALC is transforming the laser community in Africa. There's another laser network called LAM, which is led by Professor Amadou Wage, who's the president of the African Physical Society. And so we will discuss that organization, discuss LAMP, the efforts to train African researchers in the use of these light sources. And then the X-Tech Lab, how it's transforming crystallography education on the continent. So there are all of these efforts going on, and I think it's important for the African leaders to know about these things that are happening. We have these synchrotron schools that are operated out of the Abdus Salam ICTP. We had the second one just in February. They run for about 2 weeks. And we had a large following, large participants from all over the world, including Africa. So that was quite a success, and we hope to do this every year. We helped to found the African Crystallographic Association and other such groups. And then chapter 7, we will discuss the statutes, the governing statutes for an African light source, and is based on studying what the ESRF did, because it's an international collaboration, and what SESAMI has done, which is another international collaboration. So it's very, I'm sure this will have to be tweaked by the African Union, but at least we did the best that we could, trying to incorporate best practices from previous groups. And then chapter 8, we will talk about our prototype, 4th generation African light source and all that goes with it. One of the interesting things is the electrical power. SESAMI is the only light source in the world that's fully solar powered. Okay, and so that's a great, Africa has a lot of sunlight, so that's a good thing to incorporate. And it would take about maybe, as far as we can understand, about 5 megawatts to power the facility. However, one of the great things about these light sources is that they tend to generate a campus around them. And this is the campus around the Diamond light source. So industry will start co-locating there. They have over 100 companies that are co-located there. And so university labs will come there. So that's why on the previous slide, we're saying that you're probably going to need maybe 10 megawatts, because you have to more than just operate the facility, but you will have to operate all the other facilities that will be coming. And in addition, if there's leftover power to the community, to the greater community. And then finally, we will talk about some experiments done by various researchers, mostly from Africa, that were sponsored by the LAMP project. And I think that is the end of the African light source. And so finally, I want to leave something with you. There's now a movement that's gathering. It's very early on, and we've discussed with Professor Rabinovich, we've discussed with my dear colleague from Department of Energy. He's here, Dana. Is it Kibney? Your last name, is it Kibney? Kibney, right. So we've discussed with them. We went to, we've discussed with officials from the National Science Foundation, but this is very early now. It's being led by Leo Violini, who lives in Rome. And there's a Victor Del Rio, who lives in Australia, who's originally from Mexico. So the three of us are trying to push to see if we can gather some momentum, because it would be great to have an African light source in the greater Caribbean. As I mentioned before, in the very first slide, I showed you that there's only one light source in South America. Now, the key is that it only has a 3 GeV accelerator. And so Harry Westphal, the director there, said it would be a great idea if a lower energy light source, a 1.5 GeV, that's more optimized for infrared, could be built and operated in the greater Caribbean region. So that's sort of the idea there. They have the 3 there and the 1.5 in the Caribbean. Now the Max 4, which is the light source that I told you ushered in the 4th generation, they have both rings. You know, they have the 3 and the 1.5. So that's where we are with that, and I think I can conclude, and thank you.
Thank you for that. We have questions.
Over here.
Thanks for the presentation. Can you give some context into the approach that science funders in Africa take with respect to these large projects, given the broader fiscal and macroeconomic environment?
Yeah, you know, a lot of it some of it is led by organizations like the African Academy of Sciences. I know in South Africa, there's the South African Institute of Physics, which is their version of our APS. So generally, these organizations will try to, lobby the government officials. You gather interesting contacts. In fact, one I can tell you about, the African Laser Center that we started in 2002, the head of that was a guy named Philemon Mjuaha. Okay, so I worked very closely with him on that. He has now, for the last maybe 10 years, has been Director General of South Africa Science and Technology. So he's a high, but I have to be very careful when you have friendships with people. You don't want to abuse your friendships. But we have a lot of people in high places who we can actually talk to and try to push these projects forward. Yeah.
Thank you. Any other questions?
And I might mention, Christine is also working with us on this conceptual design report. She's made important contributions.
Thank you. So where would you see the biggest synergy between the Sesame and the African light source?
Where would I see what?
In terms of synergy with people, with hardware?
Yeah, well, it's a lot of synergy already. I mean, for instance, Andrea Lauzi, who is the scientific director at Sesame, we work together in the synchrotron school that we sponsored. We work together. Almost all of our conferences he tends to come to, and he has some of his chief scientists, Jihan Kamil, who does the infrared beamline there. She's very active in what we do. In fact, she's on the executive committee of the African Light Source. And then there's Masoud Hafoush, who does more, I guess, X-ray absorption spectroscopy. He's involved. So we all work very close with each other. So that's one of the reasons why, you know, some of us are working trying to get the injector for sesame. So we kind of work very closely with each other. Yes. Oh, I think I'm in trouble now. If Prof's going to...
Well, actually, I would like to say thank you to Sekazi before I say anything, because Sekazi did a lot of work. We, the younger generation, when we came into the project, Sekazi has already done, and Simon, they have already done a lot. We are just following the footstep of what they have prepared. I think in one of the graphs, he showed how things started around 1990 and all the way, and when we came, a lot of things have been done. Then a small question, Sekazi, is now we are talking about African light source and we are sitting in the US. So how do you see also, Christina talked about the synergy with Sesame. What about the synergy with the light sources in the US towards also contribution to the African light source project?
Yeah, they actually have been quite active. You know, in the LAMP program, we've sent people to the advanced photon source in Argonne. We've sent people to the advanced photon source, the advanced light source in Berkeley, at Brookhaven. In fact, you know, Brookhaven, Shun Shin, who's the scientific director there, he's been very active. And I actually, you know, I have a company and I do work with Brookhaven. And from that, I've gained great contacts there. And so Brookhaven is fully aware, and the people there are very interested in the African light source. So yeah, the synergies are strong. It's amazing how scientists so want to work together. I remember as a young physicist at Fermilab, I worked in the old days building stochastic cooling systems there, and we had people coming over from CERN to assist us. I mean, you compete against people, but yet somehow we're able to all come together. You know, they come here, they help us, we go there, we help them, you know, but, you know, that's the way it is. So there's so much synergy in the scientific community. So we try to stay away from politicians as much as we can. We just want politicians' money because they like fighting.
Thank you.
Yes.
Thank you so
thank
much.
you, thank you, thank you.
Thank you, everyone, for attending this session.